just to share with you some of my general thoughts about why we organize this event and why this is now very important. We know that the energy use, energy consumption, and types and volumes of this use is an indicator of the level of economic and social development of both humanity as a whole and each country in the world. So, in my understanding, it is probably the most important attribute of development. The atmosphere and the ocean are the most important attributes of life. The atmosphere provides the necessary gases for existence of living things and provides thermal regimes, smoothing out temperature fluctuations. And the ocean is, of course, the cradle of life. And we know very well that in the search of extraterrestrial civilizations, we first of all turn our eyes to exoplanets where there is an atmosphere and where there are oceans. And in the 20th century, we saw, and in the 21st century, we actually felt that these attributes of life and attributes of development can contradict each other. By producing the energy needed for development of industry and to improve our life, we began to heat up surrounding space directly or indirectly due to imbalance of greenhouse gases. Moreover, the beginning of a significant industrial effect on the thermal regime of the planet occurred not far from the temperature peak in the Milankovitch cycles. And it happened very quickly on the scales of decades, few decades, in comparison with tens of thousands of years of natural fluctuation in the thermal rhythm in these Milankovitch cycles. And the most important challenge facing now our planet Earth is whether it will be able to adapt to this abrupt endogenous push in the global stage, or it will go to some unknown states which can threaten with dramatic and possibly catastrophic consequences. Concerned humanity tried to agree on the global level. We well remember Kyoto Protocol, Paris Climate Agreement, and now European cross-border carbon taxation and so on. But we know also that there is a price for use also in nuclear energy and wind energy. Nuclear power leaves some nuclear waste, and wind energy has an impact on ecology through inevitable excitation of some mechanical movements in the environment. And the search for this relationship between global energy and climate change, actually, it is a kind of very interesting problem for many scientists, physicists, geophysicists, chemists, even economists and lawyers. There are many questions to answer: how to reasonably reduce the impact on global energy, on the climate without hindering the progress. What is the role of natural factors, in particular permafrost melting of the global energy balance? Is there a positive feedback in the development of warming processes in nature? Is clean nuclear power possible, and so on? And we are planning to discuss all these issues today. And actually, what I think, if this discussion is successful, we probably may in the future continue this forum by new sessions dedicated to some specific issues. Before giving the floor for short introduction to our other chairs, I would like first of all to introduce Toshi Tajima, professor of the University in Irvine. Toshi is an outstanding physicist in the area of plasma physics, laser physics, astrophysics, study of extreme states of matter. Toshi worked quite long time at the University of Texas, where we met several decades ago and made our joint first publication. Toshi is now distinguished professor at the University of Irvine and also the chief scientist of Tri-Alpha Energy. Toshi will chair the first part of our forum. And the second person I would like to introduce is Professor Valery Rubakov. Valery is the academician of the Russian Academy of Sciences, an outstanding scientist in the field of high energy physics, and also editor-in-chief of the journal of Успехи физических наук, how it just is called in Russia. It is Russian Успехи in physics. And Valery agreed to provide the page of his famous journal to publication following this forum. So, welcome my dear colleagues, co-chairs, and first of all, probably Valery will tell some words.
Yes, thank you. And I just want to say that Physics Успехи is very glad to be associated with this forum, with this meeting. I hope this meeting will be fruitful, really, and interesting, productive, and we're happy to provide the coverage of this meeting, the space for written versions of the talks. Of course, this is interdisciplinary meeting, and somebody should take this role. And I'm glad that two physicists, Toshi Tajima and Alexander Sergeyev, initiated this forum, this meeting, and agreed and addressed Uspekhi to give the coverage of this meeting. So I'm very glad. I welcome all the participants, all who are with us on Zoom and also on YouTube. And I wish the meeting all success, and we will be glad to publish its proceedings. Thank you.
Thank you. All right. Following Valerie's introduction, let me also introduce what I have been involved with Sasha. This is Toshi Tajima, Norman Rostock, Chair Professor at University of California, Irvine. Sasha and I have been also working on the international project, like International Committee for Ultra Intense Lasers. I have been chair of that for I think 8 years, and I also inducted Sasha into co-chair while I was serving the chair. So we are working global aspect of various science in that field as well as others. 2 years ago, Sasha asked me that if I can serve some function to make a forum in Moscow on this subject. And then at the time, I thought that I was not quite able to travel. It was before COVID. But after COVID, it even worse. So it became a Zoomed meeting like this, which permits us to meet relatively easily. And I'm very glad that many people accepted. And then also publish it thanks to Uspekhi kindly and very prestigious, one of the most prestigious physics review journal of the world. I'm very glad that you guys allow that kind of a privileged place for the speakers to publish their own papers ad infinitum, because the speech can last only 10 minutes or 30 minutes, but the review paper lasts forever, right? So I'm very glad that we have double punch, speech and the paper, review paper. Okay, so having said that, since I'm serving the first half of the conference chair, followed by Sasha in the second half of the conference. So without further ado, I would like to invite the first speaker of the first part of the session. First 5 sessions are mainly climate climatological issues of global warming and the other impact that the humans have created. And the second half will be the energy issues or energy solutions, how to handle this. And so these are 1 and 2 parts. In the first half, I will serve as chair. Before I just start, I kind of remember that 1956, Russians at the time called the Soviets, and then the Americans and the other Westerns have been in the Cold War. But in 1956, they decided to get together in a scientific way in Geneva, Switzerland. And then they convened the various, Cold War melting meeting, which launched the various things such as fusion declassification and other things such as Wechsler's famous collective accelerator idea. These things have been floated in 1956. So at the time, West and East rapprochement allowed the science to spurt. Now, I hope facing this global crisis, we can solve once again by meeting like this. So here's the first speaker by Igor Semilotov, head of Arctic Research Lab of Russian Academy of Science. Please.
Dear Alexander Mikhailovich, dear Toshi, thank you very much for the invited talk, and let me start. Okay. It's well known that the Arctic is linked to the global climate system through the water cycle, the Mahalayam conveyor, and the carbon cycle greenhouse effect. There is growing evidence that thawing permafrost has the potential to affect humans outside the Arctic through increasing releases of carbon dioxide and methane. And this talk aims to discuss mechanisms of CH4 and CO2 release from thawing permafrost in the Arctic land shelf system. In this report, we will focus on coupling between climate change and permafrost thawing in the Siberian Arctic land shelf. And current concentration of atmospheric carbon dioxide and methane, main greenhouse gases, far exceed pre-industrial values found in polar ice cores records of atmospheric composition during back about 700,000 years. And according IPCC 207, post-industrial rise in these gases doesn't stem from natural mechanism, but global distribution of concentration of the main greenhouse gases CO2 and methane exhibits the existence of their maximum above the Arctic, outside the northern hemisphere mid-latitudes, where the main anthropogenic emissions of these gases are existing. And we suggest that the main source of methane, CH4, and CO2 in the high northern latitudes is related with the permafrost thawing in the Arctic land shelf system. Okay. And global, okay, the permafrost is vulnerable for dramatic +4 Celsius degree warming in the Arctic, with potentially catastrophic impacts on climate through rapid mobilization of the labile carbon sequestered in permafrost surrounded the Arctic Ocean. The past 30 years, the Arctic has warmed at roughly twice the rate as the entire globe. It has been realized that the main man-made greenhouse gas emissions are affecting Earth's energy balance, but further studies should be emphasized on understanding of natural mechanism of triggers and feedbacks of climate change. And top candidates for the potential abrupt climate change in scale of decades is thaw and release of organic carbon from Arctic permafrost in the land shelf system, which is postulated to be one of the most powerful mechanisms causing a net redistribution of carbon from land and ocean to the atmosphere. And hydrate collapse and consequent massive release of methane into the atmosphere. And full sizes of organic carbon in on land permafrost and subsea permafrost are similar. However, subsea permafrost is much more vulnerable than its terrestrial cousin because it experiences a drastic change in its thermal regime due to inundation by the ocean and consequent warming by as much as 10-17 Celsius degree prior to the current ongoing climate change. Thus, the subsea permafrost hydrate system is the top candidate for massive CH4 release in response for the long-term warming, because subsea permafrost has been subjected to additional warming by up to 17 Celsius degree during the last 20,000 years. Consequently, the subsea permafrost is present in transition from frozen to unfrozen state. And one more component of global carbon cycling late in Arctic is coastal permafrost complex, which is very fragile and also is huge. It's 400 billion tons. And to understand the Arctic carbon climate permafrost links, we focus our report study on evaluation of organic carbon pool size, its dynamics and structure, and organic matter composition, and then vulnerability of large Arctic carbon pools toward a warming induced demobilization of the sleeping giants of the global carbon cycle. One possible climate feedback is release of previously produced CH4 preserved within seabed deposits, such as natural gas fields and coal beds, and collapse of the CH4 hydrates underlying the Arctic seabed. Some authors still doubt the significant climate role of methane release from the subsea permafrost hydrate system, because they don't see proxies of permafrost hydrate CH4 release in the ice core data archives for penultimate interglacial epochs. However, it has been shown that the current interglacial period is unique because the climate system for about 6,000 years is delayed beginning of the coming cold epoch after the Holocene optimum, keeping high sea level stand. So it's well known that a climate cycle, it's roughly 100,000 years, and at least for the last 450,000 years. But this cycling was broken since Holocene optimum. And since then, global sea level is near stable. So that means that high stay of sea level was extended for 6,000 years. That is crucially important for extra destabilization of the subsea permafrost hydrate system. And the Arctic Ocean is unique because it's only one ocean which is surrounded by permafrost, which is being degraded at an increasing rate under conditions of warming. The Arctic land shelf region contains a huge amount of organic carbon which could become involved in the current biogeochemical cycling due to thawing of on-land and subsea permafrost. And permafrost thawing increases also the river freshwater discharge and heat discharge, which causes significant warming of the shelf waters accompanied by shrinking extent of sea ice. And why we focus our study on the East Siberian Arctic shelf? This is because the East Siberian Arctic shelf is the broadest and shallowest shelf in the world ocean, where about 80% of predicted subsea permafrost and Arctic hydrate deposits exist. This region, East Siberian Arctic shelf permafrost stability is the key to whether preformed CH4 sequestered in hydrate deposit escapes to the water column atmosphere. Most of this region is shallower than 50 meters, which is an important factor for rising CH4 bubbles to reach atmosphere, avoiding dissolution. And sedimentation on the East Siberian Arctic shelf is determined by combined input of coastal erosion and fluvial sediment discharge, which are also driven by current warming. This slide illustrates that projected extreme warming in the end of this century is most pronounced in the East Siberian Arctic region. And note that in spring, March, April, May, air temperatures in this region had already reached this projected temperature. We are already there. We focus our observationally based study on potential impacts on climate through rapid mobilization of labile reservoir sequestered in the Arctic land shelf permafrost. In this study, we consider the East Siberian Arctic shelf as integrator of transport and fate of terrestrial carbon from fluvial discharge and coastal erosion. And subsea methane sources are considered separate. It has been 2 decades since investigations of terrestrial organic matter sources and CH4 emissions from the East Siberian Arctic shelf and other Russian seas began by our international team. It has been as the last 2 decades, about 49 expeditions were conducted, including marine cruises and river cruises along the Great Siberian rivers, Lena and Tok, and in summer, and oceanographic expeditions drilling from the fast ice in winter. Thousands of water, sediment, and gas, and countless air samples were collected and analyzed to evaluate first the variability of dissolved and atmospheric CH4 in different areas of the East Siberian Arctic shelf, to assess the isotopic signature of contribution sources using triple isotope analysis. And the second topic is transport and fate of terrestrial organic carbon. Advanced geochemical techniques, including molecular and isotopic, were applied. As a result of this effort, an unprecedented data set was accumulated. It provides the best coverage ever reported for any area of the world ocean. Let's start from the first topic. It's rivers, fluvial discharge. We used Arctic rivers as natural integrator of permafrost derived organic carbon release in their huge watersheds with a total area which is about 14 million square kilometers, which is comparable with the entire Arctic Ocean. And we use these watersheds as integrators to resolve between surface versus deep sources. With molecular, we use molecular composition and radiocarbon edges of different compounds to identify the driving sources, the main sources. And it has been found that less degraded terrestrial organic matter was exported from river watersheds with more extensive permafrost, with trends in degradation status of terrestrial organic matter from west, Open Yenisei, to east, Lena, Indigirka, Kolyma. It means that more terrestrial organic matter could be oxidized to CO2, to carbon dioxide in the Siberian Arctic, comparing with the Kara Sea. Different permafrost carbon pools respond to different landscape changes. And in present, dissolved organic carbon and river particulate organic carbon oxidation to carbon dioxide plays an important role in biochemical processes. But it doesn't contribute significantly to regional air CO2 balance. And rivers are small sources of CH4, of atmospheric CH4, because of oxidation in fresh water is very effective. And let's move to the second topic. It's effects, climate effects from coastal erosion. Strong eroded carbon export can be seen from satellite images. And it has been shown that eroded and topsoil, its fluvial input carbon, dominates in the shallow East Siberian Arctic shelf zone, but marine originated organic carbon impact is increasing northward from the mid-shelf. It was suggested that more than 20 million tons of terrestrial organic carbon is delivered to East Siberian Arctic shelf each year. And such a high level of sedimentation contributes to thickness of the sedimentary basin, which reach up to 15 kilometers, providing favorable conditions for CH4 production in seabed in this area. To compare, so in other shelf areas, it's several times less. It's 2-3 kilometers thickness of sedimentary drain. And it has been found that the western biogeochemical province of the Siberian Arctic shelf, which is strongly impacted by river runoff and the export of eroded organic matter, is a source of atmospheric CO2 because of oxidation of eroded carbon to CO2, while the eastern province is a sink. And roughly 10 million tons of carbon dioxide is released annually, actually in summertime, from the sea surface, from the western province into the atmosphere. And pumping of organic matter in the Siberian Arctic land shelf system with coastal erosion and rivers plays a key role in export of old permafrost-derived organic matter, sedimentation, and water biogeochemistry. However, in present, climate impact from river and eroded organic matter transformation and consequent CO2 and CH4 release into the atmosphere is small. Sorry. But massive permafrost organic carbon remobilization was found during the early Holocene. Then warming by only a few degrees, pending warming about a few degrees, may abruptly activate large-scale onshore permafrost thawing, indicating a sensitive trigger for permafrost climate change feedback. Let's move to the third topic. It's hydrate topic and massive methane release, how it would impact the current climate changes. And the amount of organic carbon preserved in this Siberian Arctic shelf is large enough to provide a substrate for CH4 production, which makes the East Siberian Arctic shelf as the largest and arguably most vulnerable stores of subsea methane in the world. Different models show that the East Siberian Arctic shelf subsea permafrost would work as the lead impermeable for gases. It's left map. or show discontinuities only in the areas of rifts with high geothermal flux. Right map. However, the observations show CH4 release from seabed across the Siberian Arctic shelf, not only in the rift zones. And distribution of dissolved methane shows that the Siberian Arctic shelf serves as a significant source of CH4 to the atmosphere. The
So
first
5 minutes to go, okay? 5 minutes for your talk part, okay?
Let me move to the next slide. And observation of methane release from East Siberian Arctic shelf and high methane concentration in the water column and air above have been attributed to gas pathways created in Soviet permafrost. And based on our force 17 boreholes and literature data, we suggest that the table of subsea permafrost has already deepened to depth 100 meters and deeper. And downward movement of the ice-bounded permafrost table is roughly 14 centimeters per year and several times higher than it was assumed before. This slide clearly demonstrates that bubble induced methane evolution is associated with gas wetting from seabed deposits. This slide demonstrates that bubble-induced fluxes is a predominant contributor to CH4 releases in the East Siberian Arctic shelf. It can be seen that observed routes of gas pathways would provide CH4 flow from sediment depths in from several kilometers with diameter from several meters up to 500 meters. And new mechanism of methane release was discovered, which shows that gas front is moving upward with annual rate up to 7-8 meters. And before it was supposed that the upper reflection boundary is supposed to be represented as subsea permafrost table, but our drilling testing demonstrates that that gives a jumping towards a jumping increase of dissolved CH4 in pore water. And another natural mechanism of CH4 release is ice current, which reaches the gas front and uncork bubbling CH4 release as it works like opening a bottle of champagne. And this slide show pre-storm and post-storm dynamics of methane and atmospheric CH4 mixing ratio. Increasing concentration in surface water and air were caused by pumping of CH4 from sediments and wind-driven ventilation. And to quantify CH4 fluxes being released from seafloor, we implemented a downscale to upscale approach to interpret sonar data. We performed an in situ calibration that aimed to establish a relationship between the backscattering strength of CH4 bubbles and gas flux. Based on multi-year in situ calibrated data, we suggest that the range of CH4 evolution is 5 orders and higher. The current observation-based emission of CH4 from the Siberian Arctic shelf was conservatively calculated to be between 8 and 17 teragrams annually. But this value is strongly underestimated because of massive release from more than 1,000 large ships and mega ships discovered in the years later was not included in this estimation. And CH4 release from the Siberian Arctic shelf is comparable or even exceeds annual anthropogenic emission in the United States, which is ranged between 22 and 32 million tons per year. And the isotopic signature of dissolved and bubbled CH4 gives mixture of both possibly thermogenic and biogenic sources. at places where subsea permafrost thawing in the Siberian Arctic shelf occurs, in the areas affected by faults, paleocanyons, and pre-existing thermokarst, and where occurrence of deep open talus could be expected. CH4 would be released from hydrates. And new challenge and 3D electromagnetic polygon surveys shows existence of shallow pockmarked craters in the East Siberian Arctic shelf, right, and near Yamal Peninsula, left at Skara. A geological mechanism and physics of this formation, of their formation, is still poor known. And some models gives estimate that impacts of carbon dioxide and methane released from thawing the permafrost would cause economic impact, which will cost up to $43 trillion US. Another models published in Nature gives even higher value, up to 70 trillion US dollars. And conclusions: Siberian Arctic land shelf is a key region to study climate carbon permafrost interaction. Amount of preformed gas preserved in this region suggests the potential for possible massive abrupt release of CH4, whether from destabilizing hydrates or from free gas accumulation beneath subsea permafrost. Such a release requires only trigger. Understanding the role of seismotectonics and gas release as a trigger needs further comprehensive studies. Sustained release of CH4 from East Siberian Arctic shelf is a positive feedback to climate warming. We are moving closer to system understanding, allowing predictive capacity of future greenhouse gas fluxes. And sedimentation and major biochemical processes on the shallow East Siberian shelf are driven by coastal erosion and river impact. And physics for the formation of focused gas pathways across the subsea permafrost is unknown. One more emerging challenge. And bottom line, Russian international community has golden position to lead breakthrough science as the coming years during the Russian presidency in the Arctic Council and beyond. The coming potential opportunities, pending Arctic Council project gas hydrate and annual expedition to the Siberian Arctic shelf and Kara on board Russian research vessel academician Vyacheslav Keldysh, and joint expedition with Esverus. It's a Swedish, Russia, US program in framework of the Eurasian Arctic C4 program. It's supposed to use 2 free research vessels for simultaneous operations. Thank you very much.
Okay, thank you, Igor. Thank you very much. And also alerting us about the positive feedback of methane release and global warming through Arctic area of transition. All right, so any questions or comments on Igor's talk? Couple more minutes left.
Toshe, I would like to ask Igor about the water vapors, because we know that there are other ideas of this positive feedback, not only from CO2 or CH4, but also from increasing amount of vapors, water vapors in the atmosphere. Just how we can compare these, let me say, these increments of this positive feedback growth?
No, it's thank you for this equation. It's widely discussed between climate scientists and other scientists, and it's still no consensus between them, because it's just no data sets which allows us to compare, to estimate changing impact of water vapor on climate. And it's a consensus between scientists worldwide to consider CO2 and methane as the main greenhouse gases, which are distributed mixed, because troposphere is mixed well regarding CO2 and methane, but water vapor is too complicated because actually it's no data for it's very limited data sets for vertical distribution of water water vapor and its dynamics. I think that this is the reason why it's not studied so deeply.
Mm-hmm. Thank you.
All right, thank you very much. It's about 30 minutes, so it was a very good cutthroat first talk. We can follow with Igor's talk, and now the second speaker is Philippe Drobinsky, who is a research director of at École Polytechnique. Philippe?
Okay, sorry. Can you hear me?
Yes, we do.
Okay, perfect. And do you see my slides?
Yes.
Okay, great. So thank you for inviting me. And so you already introduced me. So I'm a climate scientist, but I'm also the director of an interdisciplinary center called Energy for Climate, which really makes the link between, let's say, climate variability and change and energy transition in general. And here I will focus my presentation on energy planning. So I will first start by making clear, if necessary, of course, but the link between climate change and energy. So the climate is warming up, so the observations speak for themselves. And here the figure shows the evolution of anomalies of surface temperatures compared to pre-industrial levels, average of the globe until the year 2000. And so the black curves shows the observation, and we see that first cooler years follow warmer years and vice versa. So this is called natural variability. But we see on top of the natural variability a significant trend showing evidence of a global warming that has accelerated since the 1980s. And so today, the climate has warmed by about 1.25 degrees Celsius, the latest figures issued by our colleagues of NASA. So compared to pre-industrial levels, and well, no doubt persists by emitting greenhouse gas concentration in the atmosphere. The man is responsible for this warming. So first, how are we sure that humans are the cause of global warming? And so for this, we use climate models. And so the red here and the blue curves are derived from climate simulations. And so the blue curve corresponds to simulation in which anthropogenic sources are absent, whereas the red curve corresponds to the simulation fed with the observed greenhouse gas concentrations. So the curve corresponds to the average of about 40 simulations performed in different research centers worldwide, and the envelope indicates intermodal distortion. So it can be seen that only simulations integrating anthropogenic emissions of greenhouse gas and also anthropogenic air source are able to reproduce here the observations demonstrating the role of human activities in global warming. And it is indeed observed that during this period, the CO2 concentration increased from about 300 to about 370 parts per million. And this concentration is measured at the Mauna Loa reference station in the middle of the equatorial Pacific, away from any local sources. And in 2020, it is about 414 parts per million. So we have to keep in mind that in the last 400,000 years and before the industrial era, the CO2 concentration oscillated between 180 and 300 parts per million, following the Milankovitch cycle of about 100,000 years. So there is a clear departure from this, I would say, natural CO2 concentration variability. So how this will evolve in the future? So the way this is going to evolve is not strictly foreseeable, since the trajectory will largely depend on the actions that the nations of the planet will take to reduce greenhouse gas emissions. So this time we feed climate models with greenhouse gas concentrations that are no longer observed, but that come from scenarios which are produced using demographic and socioeconomic assumptions, and they are converted into greenhouse gas emission. So it is customary not to consider one, but several scenarios. And in the figure here, the greenhouse gas, it shows the greenhouse gas emissions for the 4 scenarios adopted for the last IPCC report. And so the scenarios include emissions or concentration of pollutants, so in addition to greenhouse gas emissions, but also land use inventories and socioeconomic data, which are needed to calculate the impact of climate change. And in the last IPCC report, so these scenarios are named representative concentration pathways, referred here as RCP. These scenarios have been translated in terms of radiative forcing, which quantifies the modification of the radiative balance of the planet, which is expressed in watt per square meters. And so the higher this value, the more the Earth atmosphere system gains energy and warms up. And so the 4 scenarios range from 2.6 watt per square meters to 8.5 watt per square meters. And so this figure shows the change in global average temperature at the Earth's surface compared to the end of the 20th century for 3 of the 4 scenarios just presented. And so the curves diverge from the beginning of the 21st century. And in red, so we have the most pessimistic scenario, that is, unfortunately, I would say the one that best reflects the current situation. In blue, the scenario to limit global warming below 2 degrees C, and in yellow, I would say the most optimistic intermediate scenario. So depending on the scenario, the warming could be between typically 1 to 4 degrees on average. So the 2 degrees C limit of acceptable, I would say, global warming was set in Copenhagen at the COP15 in 2009, and was at the center of the negotiations that led to the Paris Agreement. Caution encourages to respect this limit, proposed with reference to a period of the past when this average temperature had been reached without a climatic disaster. It is not an absolute limit, an absolute value, but if exceeded, would probably increase the risk of a climate bifurcation with potentially dramatic consequences. So Article 2 of the Paris Agreement expresses the commitment of parties to maintain the increase in global average temperature well below 2 degrees C, well below 2 degrees C above pre-industrial levels, and to pursue efforts to limit increase in temperature to 1.5 degrees C, as it would significantly reduce the risks and effects of climate change. And these thresholds have been discussed in terms of risks. The threshold of 1.5 degrees C corresponds to a reduction of 45% of CO2 emissions by 2030, and the threshold of 2 degrees C, a decrease of 20%, a decrease of 20%. So, for example, here, in terms of water stress, an additional 500 million people would be at risk of water shortages. Almost 3 times more people would be affected by floods, while the fish stock would dramatically decrease. So in order to achieve the long-term temperature goal set out in Article 2, the parties strive to, in Article 4, to achieve a global peak in greenhouse gas emissions as quickly as possible and reach carbon neutrality in the second half of this century. So until 1970, about 1,000 gigaton of CO2 were emitted, and it doubled in over the next 40 years. So the total, I would say, today the emission rate is around 40 gigaton of CO2 per year. So the figure here represents the global average temperature change as a function of the cumulative anthropogenic CO2 concentration since the pre-industrial era. So we see that this is a quasi-linear relation. There is a quasi-linear relationship between these two variables and framed by an envelope reflecting the uncertainty of this relationship between the models. So this is called what we call the climate sensitivity. And so this figure shows the so this other figure shows the emission reduction between 2050 and 2010 needed to ensure compatibility with the emission scenarios. And so in order to remain below 2 degrees C of global warming, the total cumulative anthropogenic CO2 concentration should not exceed 3,000 gigatons. And so taking into account, and for this, we see that to comply with this threshold here, we see that we should reduce by about 50%. We should reduce by 50% our greenhouse gas emission in 2050 with respect to 2010 levels. So if we take into account the uncertainty of the cumulative CO2 emissions for each scenario, it appears that the emission scenarios making it possible to limit global warming to less than 2 degrees C this century are characterized by a reduction in greenhouse gas by 40 to 70% in 2050 compared to 2010. So, and we should reach neutral carbon neutrality in 2100, or at least between 2050 and 2100. So now consider the carbon budget for the 2 degrees C global warming limit. So until 2011, approximately 1,900 gigatons of CO2 were released. And so the right to emit until the 2 degrees C limit is about 1,010 gigatons, as we should not exceed about 3,000 gigatons in total, as discussed before. So at the COP21, all nations were required to submit national targets for reducing greenhouse gas emissions, referred as nationally determined contributions, or NDCs. And so given the NDCs, the remaining budget in 2030 would be 220 gigatons of CO2. And so at the current rate, it would be reached in 25 years, which is tomorrow, I would say even today, at the timescale of public policies and energy strategies. And the energy sector accounts for 35% of greenhouse gas emissions, which includes not 25% for energy production, electricity and heat production, and 10% for other energy. So reducing our greenhouse gas emissions to mitigate climate change necessarily means a profound transformation of the system of production and distribution of energy production, and a revolution in our behavior in energy consumption. So in order to mitigate climate change in the energy sector, we have to make a transition towards low carbon energy supply technologies, among those the renewable energy sources, on which I will focus my talk, as they are intermittent and depending on climate variability. Nuclear, I would say, energy will be in depth addressed in future talks. So in the 1990s, Yuichi Kaya, a Japanese economist who wanted to identify the parameters that are determining for emissions of greenhouse gas in the atmosphere, and especially carbon dioxide, derived an equation linking demographic, economic, and energy parameters. So here through the population, through the gross domestic product per capita, which measures the wealth production carried out by the economic agent, through the energy intensity of the economy, that measures the energy efficiency of an economy. So high energy intensity corresponds to a greedy energy economy for a given level of gross domestic product. And through the carbon content of the energy, which is the amount of CO2 that must be emitted to have a given amount of energy. Here, TOE stands for a ton of oil equivalent. It was just, for me, a way to represent the energy here. So this equation is used to analyze or simulate the evolution of global CO2 emissions as part of climate change mitigation policies. So to keep global warming below 2 degrees C, it is necessary, so here, as was discussed before, we have to divide by 2 CO2 emissions by 2050. So we can use the Kaya equations to see what this goal imposes on the other factors of the equation. So prospective reports on the world population of the United Nations gives a range of demographic change between 2010 and 2050, with a median scenario showing an increase of 35%. The economic growth scenarios are often published over a relatively short period of time, a few years, because the uncertainty is growing rapidly, as we saw, for example, in 2020, which was not expected due to the COVID situation. But nevertheless, there are a few existing prospective reports which point to the growth trend around 3% a year, which would lead an increase in the energy intensity of the economy of 220%. And if we finally look at the energy intensity of the economy, so the overall trend is rather bearish. It dropped by 60% between 1950 and 2010, or about 10% per decade. And if this pace continues, we're entitled to expect a 40% decrease, but the prospective reports give a 50% decrease, which is so here. And so if we combine all these numbers, we see that we need so all this means that the carbon content of the energy must decrease by 75% in 40 years, which is, of course, which reflects the magnitude of the challenge that needs to be addressed in terms of energy transition. And that's it. So to understand the issues, of course, it is important to bear in mind the carbon footprint of energy production system. So the table here shows the carbon footprint of energy supply systems from the latest IPCC report, expressed so in a gram of CO2 equivalent per kilowatt hour. And so the low carbon technologies have a much lower carbon footprint than fossil energy technologies. And here, as an example, the photovoltaic technologies are nearly 10 times less emitting than gas. And among the so-called low carbon technology, it is usual to distinguish nuclear energy from renewable energies. And so here, at least for this presentation, I will focus on renewable energies only, but once again, we will have many talks on nuclear. So when we talk about energy production, we must also include the load factor, which is a fraction, which is the fraction of time an energy supply system produces at its rated power. And so the figure here gives, in the form of box plots, the values of the load factors for different technology in the US. And it can be seen, for example, that the nuclear or coal plants have typical load factors of the order of 90%. That means that they produce at their nominal level 90% of the time. So typically, photovoltaic production has load factors of the order of 20%, which corresponds to about 25% of the load factor of nuclear and coal power plants. Wind and tidal energy have load factors of the order of 40%, with nevertheless a high variability, which correspond to about 50% of the load factor of nuclear and coal power plants. So compared to solar photovoltaic production, concentration solar power includes heat storage that doubles the load factor. So in conclusion, compared to nuclear or fossil production, it is necessary to install 2 to 4 times more renewable energy production capacity to produce the same amount of energy, which has the effect of impacting the surface required to produce a given energy. So another concept that is fundamental to have in mind is the concept of power density of electricity production, so which is the amount of power of the physical system per unit surface, per surface unit, sorry. And so the median values reported in this study give for nuclear a little over 250 watts per square meters, for coal about 120 watts per square meters, and for solar about 7 watts per square meters, and for wind power about 3 watts per square meters. So the power density ratio between nuclear and solar, for example, is about 35, whereas it's about 100 for wind. So therefore, for a given produced energy, wind technology requires twice as much installed capacity with respect to the load factor, and thus nearly 200 times more surface area with respect to nuclear and coal. So finally, to imagine scenarios of energy mix to reduce...
5 more minutes for your talk, okay?
Yeah, but that should be good. Finally, to imagine scenarios of energy mix to reduce greenhouse gas emissions without negative impacts induced from energy, environmental, and social economic point of view is far from simple. And this reflects the systemic complexity of the energy system. So we could reduce the energy transition to a constrained optimization problem. And so it is a very partial vision that largely forgets the human factor. But nevertheless, it can be illustrative. So the electricity grid must check the supply-demand balance at every moment. The demand is D and the production is P. The production is divided into several terms. So the production of renewable energy, PRES, the nuclear production, the thermal production, the imported or exported production, and the stored production or energy storage. So the major difficulty for a network operator is to be able to ensure the demand-supply balance at each moment with a variable consumption, but especially a production which becomes more and more variable and intermittent as the fraction of renewable energies in the energy mix increases. So another way of looking at things is to define the controllable energy production system as a service rendered to the grid to balance the energy, the net energy demand, defined as the difference between here the demand and the renewable energy production. So two objectives must be sought. The first aims to maximizing the penetration of renewable energies to minimize the carbon footprint of energy production. So here we do not discuss, it's not the production that we maximize, but the penetration, which is the ratio of production to consumption in order to take into account the consumption of this production. And the second objective is to minimize the variability of the penetration in order to maximize the grid stability, to minimize the costs incurred by the commissioning of controllable energy production systems, such as thermal power plants, for example. So now let's take a simple example that can be treated analytically and in which we replace the first objective with a constraint. So the constraint here is the energy production, which by constriction equals the demand, is fixed, which amounts to ignoring the goal of maximizing penetration. And so the remaining objective is the minimization of the variability of the production, the consumption being fixed. So the previous equation are simply rewritten as follows. So the constraint one says that the sum of renewable energy production, here solar PV and wind, is equal to a fixed consumption. The objective of minimizing the variability requires the covariance matrix to being computed between the load factors, here, eta PV, of wind and photovoltaic production. So by neglecting the correlations between solar and wind production, so the total variance is here as written as the sum of the variance of renewable production, each written as the square of the installed capacity WP, and multiplied by the variance of the load factor. So by applying the Lagrange multiplier method, we can rewrite the system of equations for production variance into another system of 3 equations where lambda is the Lagrange multiplier. So now let's apply this equation system to the French energy system. So the table summarizes the year 2015. So the wind and solar production. Here are the installed capacities that we will try to find with the model, and the standard deviation of the load factor of each technology. So by solving the system of the 3 previously derived equations, we obtain the solutions for the installed capacity of the 2 technologies, which depend on the expectation and the variance of the load factors and the total desired production. So if we use the table, we can calculate here the sum of the wind and photovoltaic production. which was about 30 terawatt-hour. And if we compare now, so if we apply these two equations, we obtain an installed capacity for the wind of 9.5 gigawatt and for the photovoltaic of 4.8. And so if we compare to the actual installed capacity, well, it works quite well, I would say, for a rather simple model. So now let's play a game together. Let's apply this simple model to two scenarios relevant to the French context. The first scenario is an electrical mix with a 50% nuclear share, which is a part of our pluriannual energy programming law that imposes this objective by 2035. And the second scenario aims to move the urban automobile fleet from thermal to all electric, with, of course, an electricity supply of renewable origin. So now, moving 72% of nuclear energy to 50% is tantamount to asking renewable to produce an additional 132 terawatt-hour over 1 year. And so if we apply the solutions of the model, we have we obtain an installed capacity for wind turbines of 42 gigawatt, and for photovoltaic 22 gigawatt additional. Okay, so this is this corresponds to 4 times and 5 times the installed capacity of 2050. And so if we consider the rate of deployment, the actual rate of deployment, definitely we are not able to achieve the goals of the pluriannual energy programming law, which imposes an additional 30 gigawatt in 2035. Of course, this analysis is too simple. It considers only 2 alternative technologies to nuclear, but it allows to measure the efforts to be made to comply with the national strategies. Passing the urban fleet to 100 electric translates as follows. So the transport accounts for about 30% of final energy consumption, or 523 terawatt-hour. Urban transport represents 1/3 of transport, or 128 thermal energy. And so moving from a thermal engine to an electric engine, provided that the source of electricity is renewable, so we can multiply efficiency by 3. Indeed, the efficiency of a heat engine is typically that of a Rankine or Carnot cycle, so about 30%, and the efficiency of the batteries is of the order of 90%. So if we multiply by 3 the efficiency, it allows to divide by 3 the need for electric energy, therefore 47 terawatt-hour. And so if we now apply our small model, so this is the energy that should be fulfilled by renewable energy, then we obtain installed capacity for the wind of 15 gigawatt and for the photovoltaic of 8 gigawatt, which are...
Can you conclude?
Yes, I have final slides now, which is about 1.5 the actual deployment here. So increasing the share of variable renewable energy production in the network is not simple. So it needs the sophistication of the network, which can be here divided into 4 phases. Phase 1, the low penetration of renewable is not an issue. In phase 2, the conventional control systems, such as thermal power plants and hydropower, are sufficient to integrate variable energies without having to transform the network. But after phase 3, investments need to be made to transform the network to make it smarter, more flexible, to manage the supply-demand balance with much more variable net energy demand. So just as an illustration, in France, we are here in 2017, so this is the share of wind and solar PV in generation here. And in our, let's say, national planning, we should reach 70% in 2030, which means by improving our network consequently. And with this, I thank you for your attention. And yes,
all right, thank you, Philip. It's a coupling between the balance between the climate changes and how to cope with it. Very good start of overall theme. However, time remained for the questions. Unfortunately, it was exhausted. So if you do have questions, please direct chat questions to him so that he can maybe chat back on the chat function, okay? So that we can preserve the rest of the time in the real Zoom conference, all right? So I hope it will work. All right, so the third speaker is gonna be Eric Rignall, who is a Donald Bren professor at UC Irvine, and he will talk about the impact of global warming on sea level, etc. Okay, Eric, please.
I forgot to mute myself. Can you see my slide and hear me?
Yes.
Okay, thank you. Thank you for inviting me, Toshi. Thank you for everyone to join this meeting. I'm going to talk about an impact of global warming on sea level. Several points I want to illustrate. It takes a long time to raise sea level, and it's going to take even longer to stop it. So I hope that this talk is a motivating effort for very strong action on the way we produce energy around the planet, but also to point out to you that from what we see happening in the ice sheets, having a clean energy production, it will not be enough to solve the problem. Antarctica has about 60 meters of global sea level rise equivalent locked in the ice sheet. Greenland about 7 meters, and all the 200,000 world glaciers and ice caps have about 0.5 meter. I will talk a little bit about the records from the past, show you what we know about the present, what the driving processes are and what it means for the future. And then I will talk a little bit about adaptation and mitigation of sea level rise. So we know from the Polar record how the sea level varies with global temperature. Typically 20 meters of sea level rise per degree of warming of the planet. So if we consider that we're going to warm up the planet by 2 degrees or so, 2.5 degrees maybe by the end of this century, that means that the end state of sea level on the planet should be about 40 to 50 meters sea level rise, right? So we know that from the Polar record. What we don't know from the Polar record is how long it's going to take to get there. So right now the projection for 2100 is 1 meter, because we know it takes a long time to melt these ice sheets under a warmer climate. But the end state is not going to be 1 meter. The end state is several 10 meters of sea level. So we need to keep this in mind. Another important finding from the Polar record is the rate of sea level rise. We know that there was an event about 14,000 years ago, which is called Meltwater Pulse 1A, where sea level rose about 4 meters per century for several centuries. Right? So this is not a model projection. This is not science fiction. It's something that happened in the past and is well recorded. And we don't know exactly how this happened. But this is caused by ice sheets, by the big ice sheets in the northern hemisphere and parts of Antarctica that decayed very rapidly during the deglaciation. To put things in perspective, 4 meters per century is the rate of sea level we would get if we were to speed up all the glaciers in Antarctica by a factor 8. Right? And it's possible to do that. We saw that in the wake of the collapse of ice shelves in the peninsula. We saw glaciers speeding by a factor 3 to 8. So if this was applied to the whole Antarctic, we would raise sea level by 4 meters per century. Right now, we are rising sea level 1 meter per century. But as a glaciologist, I'm worried about the possible runaway mechanism that could create these conditions for several meters of sea level rise per century. What this means for us is that we have much less time to adapt when the sea level rises so quickly. The traditional view we have on melt and how the models account for it is melt from the surface, melting of snow and ice. Ice has a lower albedo, and then you have water of the ice sheet makes even lower albedo. That's about half of the signal in Greenland. It's not the signal in Antarctica because there's not enough warming yet in Antarctica to melt the snow surface. There's also a concept out there that this water can reach the bed and speed up the ice towards the ocean. And we know from the past 20 years of research that this is not the case. This is just a little disruption on the main way that these ice sheets are decaying in the ocean. Antarctica looks like a white continent to the human eye, but if you apply radar imagery, you can see the flow of the ice from the continent into the glaciers and upstream here shown with bright colors, because that's where the ice is flowing fast. So these are the rivers of ice that discharge ice from the continent into the ocean. These rivers of ice play a fundamental role because you can change their speed under a warmer climate. And if their speed changes, I mentioned the case of glaciers in the peninsula speeding up by a factor 10, then you can have a very rapid rate of sea level rise, much faster than if you melt the surface. Melting the surface is a very slow process. You cannot speed it up as much as you want, but a glacier can flow much faster than what they do today. Typically today, the Antarctic glaciers are flowing 10 times slower than Greenland. So you could imagine that if the Antarctic was moved into a warmer climate like Greenland, the glaciers would flow considerably faster and raise sea level. Then the glaciers reach the ocean. They break into icebergs, which is my next slide. This iceberg here is 1 billion tons of ice. Greenland currently discharges twice the amount of ice that it should to maintain a state of mass balance. It discharges 200 of these icebergs every year. And to put things in context, only one of these icebergs would be sufficient to provide fresh water for a large city like Los Angeles or Moscow for 1 year. You would need one iceberg like this and melt it to provide all the fresh water you need. So there's a lot more ice, of course, in Greenland than that, but on the human scale, the loss of mass from this ice sheet is very. How fast the ice sheets are losing mass today. We know that from a satellite altimetry mission. We know that from comparing the amount of snowfall with how much is discharged by the glaciers. And we know it even better from gravity missions like the GRACE gravity mission that actually measures the change in mass of the ice sheets directly from the change in the gravity field. It does that for the Antarctic, for Greenland, and also for all of the world glaciers and ice cap, which would be extremely difficult to do with another means, whether it's field studies or airborne campaigns or altimetry. The gravity method is very spectacular for that. So you see these plots here that show how the mass is changing with time for Greenland, for Antarctica, and all of the world's glacier from GRACE. You see a map here showing in red where the mass loss is concentrated in these ice sheets. You see that it addresses all of Greenland, and in Antarctica, there's some sectors of West Antarctica and the peninsula, and some sectors of East Antarctica. You see that this curve of mass change are not linear. There's some curvature. That means that the mass loss is increasing with time. It's not a constant process. And if you extrapolate this rate over multiple decades, you see that we have about 80 centimeters of sea level rise by 2100 from all these ice sheets. And then you add thermal expansion to that. So we are currently proceeding at a meter per century sea level rise. There's going to be ups and downs, of course, in the climate system. So you need a long record for that. But the record that we have here, at least on this view graph, it's actually longer than that now, but is clearly illustrative of the trend. Now, to put that in the context of climate projection, this is an example here. You have these different scenarios of a low emission, mid emission, and high emission. And the black curve that you see over here is our current trajectory. And that's a little bit of a misleading aspect of IPCC, in my opinion, is that when we look at this climate projection, we tend to forget that we are currently on the curve of maximum rising temperature. We have not looked at a scenario where we could try to burn even more than what we do today to see what would happen. Right? The current trajectory of the Earth is on the worst case scenario of carbon emission. And we have these other scenarios by which we apply carbon emission restriction, but we are nowhere close to these scenarios right now. Right? So we should not forget about that. We are currently on the worst case scenario trajectory. Now, a big discovery of probably the last 20 years, looking at the ice sheets melting so quickly and in advance of what model projected, is that a driving process of the decay of this ice sheet is the ocean, and it's not something that was well represented in the models. Climate models for a long time have projected ice growth in Antarctica from a warmer climate because there's more evaporation from the ocean, more precipitation on the ice sheet, and not enough warming to melt the surface of the ice sheet. Therefore, Antarctica should be storing sea level rather than releasing sea level. Well, what observations show is that's not the case. Antarctica is losing mass, and it's losing mass at an accelerating rate. And the reason for that is that the glaciers are being attacked by warm water. That warm water is around Antarctica. It's always been around Antarctica. It's the Antarctic Circumpolar Current. It's been around for millions of years since the Drake Passage opened up. It's at depth, several hundred meters below the surface, so you won't see it at the surface. You have to dip instrument 700 meters below the surface, but it's circulating around the Antarctic in a clockwise fashion, pushed by the winds. And these winds have been strengthening with time. And because of the Coriolis force, they tend to push the surface waters to the north and the bottom water to the south. So more warm water gets to the Antarctic without warming the Antarctic Circumpolar Current itself. It's just the wind pattern changing and pushing the warm water more against the Antarctic than it did in the past. And this affects, of course, the parts of Antarctica that are closest to the sea, to the warm water, which is West Antarctica and the peninsula. And this sector of East Antarctica, which our Russian friends should be very familiar with because there's a few Soviet stations there, the Mirny station in particular, where there was a very active glaciology program in the 50s. I don't know exactly where it is now in Mirny, but this is one of the key areas in East Antarctica. This sector is close to the circumpolar water and has very vulnerable glaciers. So this warm water cuts the ice at the base. And this is the most efficient way to disturb the glaciers because by removing that ice near the base, you remove all the basal friction, the resistance to the flow of the ice from frictioning on the ground, which is the main reason why the glaciers don't flow faster. So we directly remove the plug in front of the glaciers from this warm water very efficiently. And very few ice sheet models represent that process at present. Now, not all of this is new. There's also the theory of marine ice sheet instability that came out in the 50s and 60s and 70s by theoreticians, which shows that if you have an ice sheet resting on a bed that goes up in the inland direction, you have a stable configuration if you melt the ice. But if the ice sheet is resting on a bed that is sloping down in the inland direction, you have an unstable configuration, meaning if you start disrupting the glacier, it will keep retreating until it's a floating ice shelf. There's no stable state in between. If there's a bump in between, it will slow down the retreat. But if there's no bump, physics says you cannot keep this ice sheet stable. The only reason some of these parts with a downward sloping bed are still around today is that there are some ridges that block the ice here and there. So if this ice is liberated from these ridges, it will go into an unstoppable retreat. And the way climate is acting on these ice sheets is melting ice at the bottom from a warmer ocean and triggering instability of these glaciers. Okay, now where are the dangerous sectors in the ice sheets? I'll start with Greenland. We have on the right here 3 large basins that are submarine, that have some retrograde slopes in them, but submarine means that if they retreat, the ocean will follow them and keep melting them at high rates. There's a 3 system, the Jakobshavn, the Njergåfjärs Fjord and Zachariastrom on the east, and then the Petermann-Humboldt on the northwest. They contain about 2 meters of sea level rise. Jakobshavn lost its floating protection right now. It's retreating at 0.5 kilometer per year. Zachariastrom lost its floating ice shelf and is retreating also at 0.5 kilometer per year. Njergåfjärs Fjord still has its buttressing ice shelf and is not retreating very much yet, but is melting under the action of a warmer ocean. And Petermann and Humboldt, Petermann lost a third of its ice shelf. Humboldt had a small ice shelf and lost it. These glaciers are retreating actually at 0.5 kilometer per year for Humboldt, which is a very high rate, right? 0.5 kilometer per year. So the floodgates of Greenland are opened up. We're not talking about the future. The protective barriers of these glaciers have been, for the most part, removed, and the glaciers are retreating down their marine basin. In Antarctica, we have a lot more floodgates. The most important one is the West Antarctic floodgate with Pine Island and Thwaites, which has a sea level rise equivalent of 1.2 meters. There are some very serious retrograde slopes in that basin. And right now, these glaciers have just a couple of ridges left before they go to a state of absolutely unstable retreat, meaning there's not an ice sheet model today that does not predict an unstoppable retreat past these ridges. The research right now is focusing on how long is it going to take to reach these ridges and what can we do to slow down the retreat once they get to these small ridges. There are also marine sectors in East Antarctica, and we tend to forget about East Antarctica. West Antarctica is lower, warmer, more vulnerable, but East Antarctica has also marine sectors, and some of them have a lot of sea level rise content. There's a lot of discussion about Totem Glacier right now, which has a 4 meter sea level rise equivalent, and Denman, which is close to the Mirny Soviet station, which has a 1.5 meter, as the deepest trough in the Antarctic. And we see the glacier retreating along that deep trough right now. So I label these with red is like the worst case, like these things are really on the way right now. They don't look spectacular, but the rates of retreat in Pine Island are 1 to 2 kilometers per year. This is very, very fast. The yellow are sectors that are changing. We see some indication of ongoing changes. They're not as strong as the red ones, but they are a concern for the future. And in the green areas, there's no indication that anything is changing right now. So the Pine Island Glacier Thwaites, I just mentioned it. This is an animation of the flow of these glaciers and the retreat. They contain 1.2 meter sea level rise. If they go down to sea, they will entrain the retreat of the whole West Antarctic ice sheet, and that's at least 3 meters of global sea level rise. Now, what we find in this sector is the glaciers are retreating at 1 kilometer per year, some of them at 2 kilometers per year, one of them at 3 kilometers per year. To put that in context, if we look at alpine glaciers, the glaciers that are closest to us, they retreat at kilometers per century. Right? If you walk in Swiss and on a trail, you will see a sign that indicates where the glacier used to stand at the beginning of the 20th century, and then you'll walk a few kilometers to find the glaciers now. In the Antarctic, we have actually the most rapid rates of glacial retreat on the face of the planet. This is the coldest part of the continent, of the planet. And this is where we see the most rapid retreat of the glaciers. It's not in the alpine glaciers, it's not in Greenland, it's in this sector of Antarctica that we see rapid retreat. And a few kilometers per year is actually at the limit of what the models tolerate. The most aggressive ice sheet model that's been published in recent years is the Desconto and Poland model, which put a limit on the retreat rate of the glaciers to 3 kilometers per year. They estimated it's difficult to conceive that the glaciers could retreat faster than that. We want to put a limit on the retreat rate of our glaciers. What we're seeing already now in 2020, glaciers in West Antarctica retreating at 3 kilometers per year. And this is just the beginning of the curve. We don't know in 40, 50 years from now how much the retreat rate could increase. We really don't know.
Eric, 5 minutes for your talk part.
Okay? Yeah. So today, 1 meter per century. Tomorrow, the possibility of 4 meters per century if a lot of these runaway processes start kicking. We haven't seen that yet. When they kicked in 14,000 years ago, there were no glaciologists looking at a record to document any of that. But the physical processes that acted back then are the same today. It's just different ice sheets, but the same physical processes. So in terms of our effort with sea level rise, there's the adaptation. I call it the ocean game. I call also this the Band-Aid solution, because it's not solving the problem. It's only working on adapting our coastline infrastructures to sea level. And it's going to be 1 meter for sure by the end of the century. It could be more if there's some runaway processes taking place in the second part of the century. Next view graph. Okay, sorry. Now, to put things in perspective, it takes 30, 50 years to put infrastructures in place. We know it's going to take some time for us to reach a zero carbon emission. It takes a while for the climate system to respond to that. Models show that it takes 30 to 40 years if you change our carbon emission. If we go to zero carbon emission today, it will only affect the climate 30, 40 years from now. The glaciers respond very quickly, and we found that Greenland and Antarctica, they responded within 15 years of the point where the climate system clearly departed from the natural variation, which was about the 1980s. So what we do now is going to affect things in the ice sheets in 50 years. That's basic physics. And zeroing carbon emission is certainly a most important goal, but it will not be enough to prevent rapid sea level rise. It will not be enough to stabilize sea level at a reasonable amount. Now you might say, there's nothing wrong about rising sea level, except that humanity built everything, all its infrastructures, assuming that sea level would not change. So I like to make this analogy with Stone Age, that we didn't end Stone Age because we ran out of stone. We should end the greenhouse gas emission age because we found something better to burn. Adaptation is good, it's creating a lot of problems, but we really need a strong policy of mitigation. And I think this is what is being talked about today, mitigation efforts. I think what I wanted to emphasize is that the goal of reaching zero carbon emission is very important, is a must be. But as far as the ice sheets are concerned, this is not a satisfactory solution to end with a planet at 2 degrees above pre-industrial. It will not stop the melting of the ice sheets, and it will not prevent multiple meters of sea level rise down the line. Thank you very much. Oh, I cannot hear you, Toshi. Maybe you're muted.
Thank you very much. Well, it is alarming scientific facts. Thank you from Eric. Nonetheless, we have to confront the fact first, and then we have to figure out what to do, right?
Yeah.
Okay. Any questions from the audience? We have a few minutes to ask him or discuss. There are chats, maybe, but okay. So if a glacial solution is so issue, what is your advice? What to do?
You mean for energy production or for glaciological research?
Yeah.
Well, okay, so two aspects important to me: glaciological research to understand what we don't know. There's a lot of work to do in the Antarctic, a lot of sectors that have not been surveyed, where we don't have ocean temperature and we don't know the seafloor depth. And we really need to have that for the models to operate. And there's a lot of unknown in East Antarctica, very close actually to, I was mentioning the Russian stations in East Antarctica. They are in strategic locations for that kind of work. In terms of energy production, I think it's really important to, as we discussed today, to look at a way to zero carbon emission. But it's equally important down the line to look at carbon sequestration strategy, because we already emitted too much carbon. We have to pay a price. We have to suck that carbon back. And it's going to be important down the line. And it's a little bit more challenging.
Okay, so that's different from a carbon emission issue, but you have to fix it. Okay,
yes.
That's a good point. Yeah, we have to.
May I?
Sure, go ahead.
Yes. Okay, so your excellent presentation, coupled with the one previous about the permafrost thawing and releasing of methane, it looks like irreversible at this point. So carbon, if net zero is not quite enough, then have you considered net carbon negative strategies that we need to be put in place in time to reverse, to stop or reverse the process?
Yes, and I don't have. That's a good question, and I don't have the answer to that. I think the rationale is that if we curb our carbon emission, if we work on carbon sequestration, we can slow down the process. Stopping is a very difficult thing, but slowing it down, buying time for us is very important. If Thwaites Glacier retreats to the ridge in 200 years instead of 30 years, that's a very big difference for humanity. So quantifying that is challenging. The models that we have now are not quite able to tell you a definite answer. So my response to engineers is work as hard as you can. You will not waste your time. You will not waste your effort. And it will pay off. But let's be realistic too. It's not going to solve the problem if in 25 years we reach the fantastic goal of being zero carbon emission energy production. We will not actually be exactly zero, but it will be a huge step forward in slowing down the process. Stopping, you want to stop it? Well, you're going to have to pay a bigger price for that.
Okay, Eric, thank you very much. I think we can go to the next speaker now. Zimfer Ismagilov, who is directing the Federal Research Center of Coal and the Coal Chemistry, and who will talk about local and global climate change impact of coal mining, etc. So Zimfer?
Yes. So, Сергей, please. Еще раз подскажите, как мне выходить? Алло.
Открывайте демонстрацию экрана. Сначала презентацию, потом демонстрацию экрана.
Вот он у меня тут.
Sorry, a little technical problem.
Демонстрации, потому что я нажал. Здесь появились мои презентации.
Окей.
Вы видите, да?
Yeah.
Не увеличивать, уменьшать не надо, ничего, все нормально.
No, all is okay.
Fine. Well, good evening or good morning, dear colleague. So it's my deeply appreciate Alexander Mikhalovich and the Toshi for invitation to participate in this conference. So I came from the okay, so okay. So this is the Federal Research Center of Coal and Coal Chemistry inside the Russian Academy of Sciences. we consist of three institutions which are well, very closely in connection with the subject of today's forum. So it's the coal mining, coal chemistry, and the humanitarian problems, environmental problems of the coal industry. And you can see the location of my native place. So this is the Kuzbas region in Chemical, which is just in the heart of the Siberia. So you can see on the map of Russian Federation. So this is the biggest coal mining region in Russian Federation, and so the subject of my talk was very broad, and I was a little bit okay. You can see well, and I was a little bit probably in the illusion that I will be able to cover in the half an hour of this big subject, you know. So nevertheless, these are the problems which appear in the terms of the terms of the coal mining, transportation, and the processing, and then, well, exactly in the what was the final words of the previous speaker was the carbon economy or carbon coal industry. So this is the typical landscape in it's worldwide the same. The open pit coal mining, which is very popular nowadays. So, and then if you look for the next slide, just I will give some short abbreviations. So here the citation from the 1937, well-known person Orwell, who wrote that our civilization is founded on coal. The machines that keep us alive, the machines that make machines, and all of the directly and indirectly depend upon coal. Practically everything we do, from eating the ice to crossing Atlantic, and from the baking a loaf to writing a novel, involves the use of the coal directly or indirectly. So it was the typical situation for decades until now, when we understand the civilization understand that the coal is the most polluting way to generate electricity. It is a serious threat to our climate. Burning coal is the biggest single source of carbon dioxide emissions from the human activity. Coal mining also releases another greenhouse gas, methane. So, and then I just have like the short citation from the United Nations Secretary Guterres, who mentioned that either we stop this addiction to coal, or all our efforts to tackle climate change will be doomed. So, in fact, this is the situation that we have if we need to stop the greenhouse gas emissions cut by 50% by 2030. So, and then we need to stop the coal combustion of the coal for the power generation. Now it will go further. Next step. This is the dynamics of the world energy balance. So we should not be very naive that we can stop the coal in the couple of years or in the 1 decade. So you can see that what is the tendency of the balance of the energy from different sources. So on the top, very small slice, this is renewable at the moment. So, and the coal still gives the 27-28% of the total need of the energy worldwide. So it's comparable with the gas and almost comparable with the oil. So this is a realistic situation today. So if you go look what's the coal situation worldwide, so this is the world coal reserves. So this is a billions of the tons, in fact, and then it will be very difficult to abandon this source of the energy. So the USA has about, well, 27%, about 18, in China about 15%, and so on. So this is a huge resource of the energy in fact. If you look for the nations who are today active in the mining and the production of the coal, this is the top list of the countries who produce the coal. So China does about more than 3.5 billion tons of the coal, and then other countries less. And you can see that it's still the huge the input into national economies of these countries. So if you look, for example, coal consumption in China, so they produce about they use the coal for the energy production, about more than 60%, and they use it for the construction. Remaining, well, the coal chemistry already they do use more than 5%, and then metal production. So this is the total balance of the using coal in China. But if you look further for the next slide, okay, so the coal consumption in terms of the only energy balance. So today it's about more than 50%, 50 to 60% of the energy is made from coal. So you can see here, and it means that more than 2 billion tons of the coal is used for the energy production. And even the perspective is not very positive, because the Chinese industry looks for the 2050 with the coal more than 50% of for the energy production. So it means that they will burn more than at least about 2 billion tons of the coal for energy production. And what is also not easy to accept, the coal generation capacities in the Asia-Pacific region looks like this. So you can see that the many countries under construction, they have this is the green, blue lines here, and then the red lines planned. So still under construction, many power plants, and also the planet for the even more for the coming next decades. That is the real situation. And then if you look at the comparison with between the Western market in the East, so it looks like this. So the blue line, which is goes down, so from 1.3 billion tons to 800 million tons. So the last 2 years. So now on the East market, the coal increases almost threefold. You can see it 3.7 times since 1990. So, and it's still increasing. So it is a realistic situation, and we have to take it into account when we are talking about the greenhouse problems globally, not only in the United States or in Western Europe. As you remember, when the Paris Agreement was signed, so we were very optimistic that it was a triumph of the multilateral diplomacy, and then we'll be very happy in the very close future. But even you can see that from this picture that even at that time and now in Paris we still have smoke, and in the other industrial countries, in Russia, so these are pictures, and in China, India, and other places, we still have very the contaminated air, mostly because of the combustion of the coal in the power stations. So I show you this picture that we have VOC concentration exceeded some days. For example, this is a very unique situation, a concentration of 16-fold higher than maximum permissible concentration. So if you look, coal, well, is the most dirty fossil fuel, and well, and then the situation is very dangerous because, as I show you already, in the Pacific Asia region, there are planned the new coal plants. Well, and then if they will be well activated, so the forecast that the increase will be not 1% or 2% or degree centigrade, but will be up to 6 degrees centigrade. So, because coal-fired power plants today give about 40% of global CO2 emissions and 72% of all greenhouse gas emissions in the electric power sector. So the next is the other technical possibilities to decrease emissions. Yes, there are. So it's shown here in scientific or technical measures which may help us to decrease the emissions of CO2. And you can see that today's situation, this is a green box on the top. So, and then you can decrease by the using supercritical steam parameters and then ultra supercritical and so on, and down to technologies for capturing, utilization and storage of carbon, which is the number 7. So by this we can decrease, but the problem of how much it will cost and who will be ready to go to these measures worldwide. Next, just to understand a little bit more, we have a couple slides of scientific. So this is the combustion of the chemical reactions of more than 200 chemical reactions of combustion of the methane, for example. And the next is what is the different, much more complicated combustion of the coal. So the much more complex. It includes similar to gas phase stages of the volatile matter combustion, the radical chain reactions, the stage of part, sharp burning, and so on, and the PM formation, which is the only characteristic for the coal combustion compared to the gas or the oil. So, and then I introduced just a couple slides from our research. So, for example, we study on the microsecond scale combustion of the coal particles by the acting emission with the pulsed near them laser in the free running mode. So by this we try to understand what is the initial stages of the combustion of the coal and try to give some recommendations for more pure combustion of the coal in power stations. So if you look at the next slide, so of course, the main product of combustion is the carbon dioxide. And then again, we come back to the comparison of the different fuels. So the coal gives, for example, 1 kilogram per kilowatt per hour, and the natural gas gives the 0.41, and petroleum, okay, 0.96. So, anyway, the CO2 production of the formation is mostly from the coal. So, and then it will go comparison in the not only the CO2 but also CO, NOx, and SOx in the particulate. It's very important because mostly people talk about CO2 as a greenhouse gas, but these gases, CO, NOx, SOx in the particulate, no less toxic and then harmful for the global warming compared to CO2. So, and then if you compare them to the example of carbon dioxide, of course, we mentioned already it's high for the coal. You can see on the red figures. So, for the carbon monoxide, the fivefold higher in case of the coal. For nitrogen oxide, it's the same. So the sulfur dioxide, of course, it's already is the subject of the coal. So, and the particulates mostly from coal, because you cannot make particulates from the natural gas or from oil. So they are shown on the left side of the slide, which is shown by bars. So the red bars are the from coal, and the black ones are from natural gas. So this is a realistic situation about the coal combustion and what are the content of the gas emissions. So again, coming back to the nitrogen oxide, so it's very important to note that if you look the two mechanisms of the formation of nitrogen oxides from chemical kinetics, so one is the Deutsch mechanism, another Finimore mechanism. So these are thermal plant and the fuel NOx. So the mostly fuel NOx is from coal, because there is in the fuel we have the chemical components which contain the nitrogen. So it's also very important to know, to understand what are the emissions from the combustion of coal. So it's shown here in the shape of bars. So you can see the bar number 4 with the coal. So the fuel nitrogens are in the green. So the highest concentration of the fuel nitrogen. What they're stressing on this subject, because the fuel nitrogens, they are in the atmosphere, they lead to the formation of ozone in the dirty atmospheric situation. So they are also very harmful for the global environmental situation. So it's again just a comparison all the different types of the fuel in terms of the CO2 formation. But if you look for the next slide, so we have seen already similar slide this evening in the second presentation. So we can see that this is the average increasing of the CO2 concentration in the atmosphere, and how the increasing of the temperature. So, you know, in the typical situation, people don't care too much about this increasing of the temperature. So, because only mostly scientific people and the research people explain this. And they even that if you look on the map of the Russian geographical map, so you can see that these are the scientific results of the measurements. So you can see that on the north area, which we have seen already from the Eagles presentation this morning today. So there degrees, 0.6 degrees increase of the temperature thus during the last 2 decades. So it's very important to know. And then again, it's not easy to work in this subject with our audience, and then even with some scientists, because they say, well, what you are talking about the global warming, when we have like the 2 weeks ago we had a -50 in our region. So today we have 26 degrees centigrade. So,
okay. 5 minutes for your talk.
Well, I still have 12 minutes. So, and then very important about what to do with CO2. So, and then like the 1,000 megawatt typical station produce about 6 million tons of CO2 per year. And then we are talking about underground storage facilities, other in deep sea, or the long-term isolation of the carbon dioxide. So these are measures. What we are not very optimistic if you are looking for the engineering side of the battling of CO2. So in this, I would like to give the very positive experience of United States, who decreased the consumption of the coal in the last 12 years. This is on the left, so you can see the total and the consumption of the coal in the green, in blue, and the right in the total in the electricity production. So, and then what is the result? Result is fantastic. I will show you Okay, I will escape these couple slides. So it says that in 12 years, so the consumption of coal was declining from 1 billion tons to the 500 million tons. So it's by half, you know, and then it gives a very good result. You can see this is the sulfate sedimentation from the in 10 years. So on the red it's the East Coast. So you can see how they improve the situation. So I mean that nature of the shortage in the consumption of the coal gives very good results in the environmental situation. Well, similar pictures we can see for India. I will escape these slides. So well, in Russia. So in Russia, well, Russia was giving the 1.6% of the greenhouse gases, and then it increased to 5.2 in 2009, and the year ago it was 4.7. But still, the leader: China, USA, and UK, and India. So this is the situation today. So the coal mining itself also gives a lot of the problems. I would like to show you. So this is a typical escape. Picture of the coal mining today. Open pit coal mining. So I will give you several pictures because we live in these places, and then I can. And then on the left, on this picture, you can see how the coal mining proceeds in these open pit mining. So a lot of explosions. We use, for example, in our region, it's worldwide the same. 500,000 tons, 500,000 tons of the TNT explosives using in this area. You can imagine again how much the global, environmental problems it gives locally, and then globally. So it's very important to know because that at least 1% of the explosives don't explode. So they are in the soil, they are in the water, they are in the atmosphere. So these are pictures from different places. So to give you imagine how is the big destroy of the land during the open pit mining. So this is the picture, the ash from the United States. This is This is smoke from coal piles. So it's worldwide again, the coal storage and then also the water. So U.S. Department of Energy estimates that between up to 1 billion liters of water per day are used in the mining and the washing of the coal in the United States. In our case, in Russia, it's the same. So it's one of the very important steps of using the coal as a source of energy. So it's shown here about how many million tons of the water, and So today is very important that I told you on the first slide is that about the exporting of the coal, and then biggest market is still today, and then it's the growing market. It's the Pacific Asia region. So and Russia exports to that region. Well, and then coming back again, just to show you on the next about the future negotiations about the Paris Agreement, there will be a big problem with these countries, Russia, China, India, and then Malaysia, and so on, because, for example, in Russia, all the coal companies are private. So it will be very difficult to negotiate about the decreasing the production of the coal because they are looking only mining and selling of the coal. We have to understand that the scientists, we have to know this. Well,
okay.
so and then I am coming. Yes, I am coming to finalize.
Thank you.
So yes, I have I still have 4 minutes. So this is I told you about water consumption, and then for example, again, I give the realistic figures. So about, for example, in our region, we use and then we waste about 400 million cubic meters of water. Of course, we start last year, we start work on this, and then scientists in the companies we work on decreasing the discharge of this water. For example, with one of the companies shown here, from 15 million cubic meters, sorry, to 0.7 in 4 years. So still work on this subject. So there is the skill. Well, and if we took in the one slide, so you can see that there are the problems of mining, processing, transportation, and coal landing. And there on the bottom, there are measures and the scientific approaches how we can solve these problems. And we'll work on this with our industrial partners. So, and then I will escape this. So, and then of course, for CO2, it is a big problem. What we will do with CO2, because as I mentioned already, these billion tons of the CO2, this will be a problem of the utilization. Well, and then of course we were looking from different countries. For example, the Japanese companies and then US companies, they propose a lot of the technologies about the sequestration and then capturing of CO2. And we are looking from our point of view, also the increase the efficiency of the combustion, abandoned coal, so storage of CO2, utilization of CO2, for example, with catalytic production of high value products. It might be the special separate lecture. And then I would like to finish with some optimistic, and then I would like to show that last year we were very happy that the president of Russian Academy of Sciences, academic Secretary, visited our region, and he visited also the coal mines, deep 400 meters in the coal mine. So you can see that with the equipment with the coal mine. So, and then it may give the good input for the research in the coal environmental problems. So, and also as soon as it was, after many years, first time meeting with all American colleagues, so I'd like to show you that in spite that we're very far away from the Moscow and other centers of the cultural and scientific development in Russia, we were very active in our USA partners. So, and we had a workshop on black carbon with the 15 delegations from USA, from the DOE, State Department, with universities and so on. It was 4 years ago, and then they were very happy to be in our city here, it's shown here, and we're very optimistic about the future cooperation. Well, and the subject will be the coal environmental problems, coal processing, and so on. So we have a good other sophisticated equipment and very nice young people, talented people. And I'd like to finish saying thank you very much for your attention.
Okay, thank you, Zimfer. I was hoping that we had a little bit more time for questions, but I think we are running out of time. So if you do have questions, send the chat, and then we will conclude the chatting with the audience at the end of the next talk, which is the end of this first section.
Okay.
All right. So I would like to introduce the last speaker of this first session, Kate McKee from University of California at Irvine. She's the chair associate professor.
Hi, Toshi. Thanks for having me and for your generous offer to give a talk today. So I'm just going to share my screen. And can you all see it fine?
Yep.
Okay, perfect. So I'm a marine biogeochemist. I study the ocean and how phytoplankton grow and affect the carbon cycle. And I'm particularly interested in how climate change is going to affect phytoplankton populations in the future. So we're going to be talking today about some of the ways that the ocean might change in the future in response to global change. But before we do that, Toshi wanted me to give some background on kind of UCI and some of our legacy in terms of studying climate change. So Eric and I are both in the Department of Earth System Science. What makes this unique, it was the first department to be formed to actually study changes to the Earth that occur on human timescales. And we're interested in looking at not only the ocean, not only the ice sheet, not only the land, but how those systems are coupled together. So we try to take a very holistic approach to things. We also have a really long legacy at UCI of innovative and pioneering scientists. On the left, we have Norman Rostoker, who was really instrumental in advancing plasma physics. And you're going to hear from Michael Binbauer later today about some of the legacy of his work. And then on the right, you have Sherry Rowland and Mario Molina, who received Nobel Prizes for their discovery of CFCs and the effect that that has on the ozone. And so the reason that I like to tell this story is because they published their paper in 1974 on the chemistry of CFCs, showing that they could destroy ozone. And it wasn't until 1987 that the Montreal Protocol was actually ratified by 197 member states. So it's an example of a very successful environmental movement. It's one of the first real strong environmental success stories. However, it did take a considerable amount of time, almost 15 years elapsed between the time that they discovered these effects of these chemicals and then the world actually caught up and started phasing them out. So sometimes environmental progress takes a lot of time. And I'd like you to keep that in mind as I go through the talk. So in the lobby of Kroll Hall, which is home to our department here at UCI, we have this beautiful, huge image on the wall, and it's of the Earth, the beautiful blue marble that we've all seen a million times. And a lot of Earth scientists think about the Earth this way because after all, we live on land and we think about the continents. But what people sometimes don't realize is that half of the Earth is actually the Pacific Ocean. 70% of Earth's surface is water. So when we think about climate change, production of carbon, production of pollutants, the ocean is actually a very large reservoir for the Earth to experience and respond to those global changes. You're probably all familiar with the Keeling curve. It's been measured at Mauna Loa in Hawaii, the concentration of carbon dioxide in the atmosphere since the late 50s. And you can see seasonal patterns every year. There's an increase and a decrease, and that's just due to summertime, wintertime dynamics in the boreal forests. But over time, we see this dramatic increase in carbon dioxide concentration. If we look into the ice cores and actually measure the CO2 in the ancient past, I'm showing this graph, it's from NASA, goes back 400,000 years. We can actually take the record back probably about twice as long as that if we want to. But what it's showing you is the cycle that some of you have already discussed in your prior talks today, that in the ancient past, we never really went above 300 ppm. Our current level is much higher than that. And that's disturbing because all of our models suggest that if we don't do anything to change our carbon production, then by the year 2100, we could have a dramatically higher amount of CO2 in the atmosphere. And the reason that's alarming is that also from the ice cores, using isotopic labels, we can tell what the temperature was in the past. And there's a remarkable correlation between CO2 and temperature. So we know that if we continue to add CO2 to the atmosphere, we can anticipate extreme climate warming. So how does that affect the ocean? What's going to happen? So we have increased air temperatures over the ocean. And sea surface temperatures as well. And these are important for weather patterns, which we'll talk about in a little bit. Biologically, we're going to start seeing tree lines shift up to higher altitudes and north as they try to stay within their appropriate climate regimes. We're seeing earlier springs, and we're also seeing animals move. And the reason that this matters biologically is because if the seasonality changes, sometimes species that depend on each other get out of sync, and then they can't survive as well. So this is one of the reasons why we're expecting mass extinctions to occur due to climate change. We also know that the glaciers are retreating, snow cover is decreasing, ice sheets and sea ice, they're all on decline because of the warming. And at the same time, we have sea level rising and increases in humidity, which can also affect weather patterns. Here in Orange County and in Southern California, we're already seeing some of the effects of this. In terms of flooding, a lot of our properties are built right directly on the coast. We have some islands and some bays where the water is literally right on people's doorsteps. Some modeling work done by a colleague of mine in the engineering department suggests that by 2050, big parts of Southern California will be flooded and inundated with water. And in fact, some of the more affluent areas are already building larger seawalls, increasing the height of their seawalls in order to prevent the storm surge from affecting their property. But perhaps more seriously, we have the effects of sea level rise on populations in the South Pacific. So this is a photograph of the island of Tuvalu, which has a maximum elevation of 5 meters. Most of it is at sea level. So with the sea level rise that Eric was talking about earlier, you can imagine that this entire nation is going to be underwater. So that means an entire nation of people are now refugees. They have to find another place to live. So it's a really big existential problem that some of us who are not so affected by the sea level rise might not appreciate, but it's an important one to keep in mind. So one of the analogies that I like to share with my students, and I think you might enjoy it too, is something that Steve Snyder, who's a scientist at Stanford when I was in graduate school, and he always described climate change as it's like the weather on steroids. So climate is like over long periods of time, the weather is like what happens day to day. And so when people say, okay, there's this huge storm happening, is that because of climate change? And so he would use this analogy. So in America, a lot of people play baseball. It's like one of our favorite sports. And there was this guy, Barry Bonds, and he was found to be using steroids. And so what Steve would say is, well, if you watch Barry Bonds hit a home run, is it because he took steroids? You don't know, because he could hit home runs before he took steroids and he could hit home runs after he took steroids. But what you do know is that the frequency and the intensity of the home runs that he hit when he was on steroids is much higher than when he's not. And that's the analogy with weather. So we can't attribute a storm to climate change, but we can say that we're going to have more frequent and more intense storms. In terms of how it affects weather, the ocean plays a really large role in affecting weather and humidity patterns because of evaporation from the ocean goes into the atmosphere, and this is what drives storms. So we know that we're going to start seeing higher storm surge, like this photograph right here. If we have higher sea level rise and then we have bigger storms that are more intense on top of it, we can expect the ocean to surge onto properties. We can expect more flooding. This is a photograph from Hurricane Katrina. At the same time, while some regions are going to get more rain, some are going to get less rain. We're going to start seeing more drought. And of course, a big one here in California, because of our drought problem, is we have a lot of wildfires, which causes a lot of property damage, but also it affects the ecosystem because then we get mudslides when the rains finally come. Okay, so back to the ocean. So the other problem with climate change is not just the warming of the water itself, but the CO2 actually dissolving into the ocean and causing acidification to happen. So the way that this works is we generate all of our CO2 and it goes into the atmosphere and it has to go somewhere. So it turns out that about half of it stays in the atmosphere, and that's the stuff that's contributing to the heat trapping capacity of the CO2 and the global warming. The other half, about half of that goes into the ocean and half of it goes into terrestrial sinks. In the ocean, it actually changes the chemistry of the water and causes it to become more acidic. So this is a graph that demonstrates what I'm talking about here. So the solid line on the top being the pH of the ocean, which is naturally around 8.2. And here we are kind of around present day. It should be a little over. We see the pH has already started to decline significantly. It's already declined over 30%. So that's a lot more acidic, especially if you're an organism that has needs to be in homeostasis. And that's being driven largely by this increase in CO2 that we see. So we know that the CO2 is going to keep increasing, and we can project that the pH is going to continue to go down. Now, this plot was actually generated in a paper when I was in graduate school. I think it was around 2005. And the reason that I like to still show it is because it's now in error. It has an error in it. And I wonder if you can spot it. I'll show you. It's here. When I was in graduate school, and that was, well, I'm not going to say how many years ago that was, but it was a few years ago. And it was at 380 was the level of the CO2. And now today I just checked, yesterday's measurement was 415. So in that short period of time, we've already increased our CO2 measurably. So this is a real problem, and it is directly measurable. Ocean acidification, I could give multiple hours of lectures on this. I'm just going to show you a little bit about it. It's important because organisms that calcify or make their shells out of calcium carbonate can sometimes have a hard time surviving when it's under more acidic conditions. So this organism I'm showing you is called a pteropod, and it's like a little sea snail. They swim around and they kind of float around in the surface ocean. And they're very reliant on calcium carbonate to protect them because it's a soft-bodied organism. And so this team did an experiment where they exposed these organisms for 45 days at the projected CO2 levels for the year 2100. And you can see the effect that it has on the shell. So over time, by the 45th day, the shell is basically dissolved. And the reason that this matters is because if the organism has to spend extra energy making new shell all the time, that's energy that it doesn't have to forage for food or escape a predator or mate. So it really is a bad sign for the species if they have to expend extra energy. It makes them less ecologically fit. And this is one of the reasons that people are concerned about ocean acidification. It's not just pteropods, there's also phytoplankton species that make calcareous shells that are being affected, as well as corals, coral reefs, which get the double whammy of having the ocean acidification on top of the warming, which causes coral bleaching to occur. So that's why that's a problem. Just check the time. Okay, cool. So I wanted to leave a lot of time for discussion about geoengineering, and I'm glad to see that people have already started talking about it in the chat. So a couple of years ago, I was at a climate symposium with an interdisciplinary group of people. And so we were talking about all of these different ways to mitigate climate change. And among them, we have carbon abatement, which is just, being more efficient with your use of energies, switching fuel types, conservation, riding a bicycle instead of driving a car, things like that, simple things that people can do. So we wanted to compare all of these other climate engineering and geoengineering techniques in an interdisciplinary way. So we were looking at things like forest management, which could be reforestation. That's when you plant trees where you've destroyed a forest. It can be afforestation, which is planting trees in areas that were not previously forests, but you're trapping carbon in that biomass. Soil management, which involves carbon storage in the soil via different farming techniques or the use of biochar, making the soil more stable so that it doesn't release that carbon back out to the atmosphere. Then we have geological burial of liquid CO2. And this is where you sequester the carbon at a point source like a factory and concentrate it down into a liquid, and then you can inject it either into the land or into the deep sea. And then we have solar radiation management, which is the idea is to reflect sunlight back into out of our atmosphere before it can have a chance to warm. And there's different ways that this can be done. You can have a marine cloud brightening by putting ions into the atmosphere. People have discussed putting large space mirrors out in space to reflect the sun. There's a number of ways that this can be done, and it's fairly controversial. And then finally, the one that I like to talk about the most because I'm an oceanographer is ocean iron fertilization. This idea rests on the fact that about 40% of the ocean has phytoplankton that their growth is limited by the nutrient iron. So they need iron as a cofactor for a lot of their enzymes. and their photosynthetic electron transport chain. And so for that reason, if they don't have enough iron, then they can't grow as fast. And so oceanographers have been studying for a long time, what is the cycling of this iron? And people thought, well, what if we just add shiploads of iron to the ocean? We could induce phytoplankton blooms. And as they bloom, just like land plants do photosynthesis and they take carbon out of the atmosphere and use it to make their leaves, phytoplankton do the same thing. They're taking the CO2 out of the atmosphere, out of the water, and they're making new cells. So now the carbon is stuck in that biomass. And so the idea in ocean iron fertilization is that once these blooms form, and the cells run out of iron again and they die, then they would sink to the deep ocean. And once those cells sink to the deep ocean, they're sequestered there for hundreds to thousands of years, meaning that that carbon is no longer in the atmosphere, it's now trapped in the deep ocean. So this would be kind of a quick fix sort of thing that you could just take a tanker out there and dump a lot of iron sulfate into the ocean, get a bloom and have a lot of carbon taken out of the atmosphere. Unfortunately, we've had about 15 very large-scale experiments that were international efforts in various parts of the world's oceans where this has actually been tried. And what they find is that, yes, you can induce a bloom, but what ends up happening is that instead of sinking, most of that cellular material gets respired by microbes in the surface ocean, and then it just outgasses right back to the atmosphere. So there's really no net sequestration of carbon. The only successful one where they saw, I think, 30% or so sequestration, they did it in an eddy, which is a swirling body of water, which is basically like it contains that water. So it doesn't let the algae disperse. It keeps it all in one area so that when they die, they actually do sink. But it would be very, very difficult to do this on a large scale. So these are the different types of things that we considered in the paper. And these are the perspectives that we took in looking at it. And one of the things that made this paper so interesting and unique was that prior to this study that we did, each individual discipline was evaluating the different geoengineering strategies independently. So the economists were talking about how much each strategy cost. And the politicians were talking about how implementable it was. And the scientists were talking about how technologically feasible it was. But nobody was considering the big picture. So our team got together and we considered these 6 different areas to evaluate each of these geoengineering strategies. So we looked at the technical potential. So how much carbon could we actually expect to sequester using each technique? The cost effectiveness, right? So how much money is it going to cost to actually implement the strategy? Ecological risk. So this is an important one too, because for example, with ocean iron fertilization, you can have unintended consequences of that action. You might select for toxic algal species that might have a bad effect on the animals that live in that area. You could cause anoxic conditions as the bloom starts to decay. And so we can't predict what those ecological consequences are necessarily going to be. For some geoengineering strategies, it's easier to tell, but for ocean iron fertilization, not really. We also considered ethical concerns. So about how is this going to affect people and non-human nature as well. Institutional capacity is the ability of a governing body to implement the given strategy. And that rests a lot on whether you're doing something locally or regionally or internationally. Because if you're doing something in international waters like ocean iron fertilization, then really it should be an effort that's agreed upon by all the nations of the world and not just one. And then finally, public acceptance is a big one. So it's not always clear what drives the acceptance of different strategies. For example, solar radiation management, which is seen by most scientists to be a terrible, terrible idea. The public is actually fascinated by it. I don't know whether it's because they think space mirrors are cool or because it just seems like it would be a rapid and cheap fix to a problem, but it's actually very problematic. So I'll show you the results of how we evaluated this stuff. So this is the paper. If you wanted a copy of it, I'd be happy to share it. The way that you read each of these graphs is the higher the amount of color is like the better strategy. So like here, forest management is very technically high potential, so it gets the highest mark. If it's low on the scale, like abatement is not very cost effective. So that's how you read each of these graphs. And what I want you to kind of hone in on is that the ones that you would expect to be pretty good are pretty good. The ones that are really, really bad in terms of our assessment are ocean iron fertilization and solar radiation management. Okay, and we can kind of talk about why. Some of the main reasons for ocean iron fertilization being a problem is that we don't know what unintended consequences there are. The public is very concerned about doing things to the ocean. They're very protective of the oceans. There's low public acceptance of it. In terms of institutional capacity, it's also ranked very low, precisely because of the reason that I mentioned, being that if you're going to fertilize in international waters, then it really shouldn't be the task of one government to decide when and where to do so. Technical potential is also on the low side because doing very broad scale fertilization efforts is hard to do. You would need a fleet of ships and a lot of iron in order to induce any measurable change, especially given what we know about the fact that most of the carbon is respired by microbes and goes back into the atmosphere. Moving to the stratospheric aerosols, or that solar radiation management, this also ranks very low. And interestingly, I think I took the slide out, but in the United States, our research council came up with, I think back in 2015, they came up with a series of recommendations on these geoengineering strategies, and they put it in a booklet, and they didn't include solar radiation management. They actually put solar radiation management in its own book to demonstrate how strongly against doing it the American scientists are. And yet, as I mentioned, people are generally pretty interested in it. It's not something that they necessarily understand. It doesn't actually address the carbon problem, for example. Like in the ocean, where we have ocean acidification, that's from the carbon. So if we start blocking the sunlight, that might be a quick fix in order to control the temperature, but it wouldn't actually fix the problem of ocean acidification, which is affecting the organisms dramatically. The other problem with solar radiation management is that it tends to not address internationally how it would be implemented. In other words, if you have one country putting stratospheric aerosols up, it could affect weather patterns in another country, a neighboring country. So there's a lot of problems with international collaboration and coordinating these sorts of ethics. So one of the reasons I think that there's such a problem with the public coming to terms with climate change and how we can get people to come together and align is that when you're a climate scientist and you're trying to talk science to somebody who's not a scientist, you have to keep in mind that they have different values, right? So some people value the economics, some people value, keeping the earth clean. Some people value, passing on a clean planet to future generations, not leaving them with a problem that's too big to solve. So when I speak to people about climate change and these issues, I like to always bring up the fact that there's a potential to create new jobs when we have a clean energy sector, transition to the green energy. If you care about preserving Earth and being a good steward of the Earth, we can talk about that once we eliminate these carbon problems, we're actually doing right by nature and taking care of the Earth in the way that we were supposed to. And that we
about 5 minutes for your talk part, okay? Thank you.
Thank you. Yes, I'm almost done. And then, like I said, not leaving our children with a problem that's too big to solve. So when we point these things out to people, it's easier to bring them into alignment, and it makes accepting the climate science a little bit more palatable. So I started the talk off by introducing you to these fellows, and I wanted to end the talk by talking about them again. And just with the perspective of, the modern environmental movement saw a success story when it came to the CFCs and the hole in the ozone. The scientific evidence came out. About 15 years later, the international community came together and decided that they were going to fix the problem. Unfortunately, climate change is a little bit different than the hole in the ozone layer. The hole in the ozone layer was letting in UV light that was causing higher incidences of cancer. It took 15 years to get on board, but they finally did it. Climate change is a very different animal. It is an existential threat to the Earth and to all of humanity, and it cannot wait 15 years. it should have been taken care of 15 years ago or earlier. And so this is why it's so dramatically important that things start to happen now, and that we start to use less carbon immediately in order to avert future changes. So I'd just like to leave you with a couple of thoughts. This is from a woman named Susan Hassel, who's a climate communicator. She teaches people how to talk about climate. And she basically summed up climate change in 10 words. It's real, it's us, it's bad. Scientists agree, 97% of scientists agree that it's human caused, and there's hope. So with that, I'd be happy to take any questions, or we can start a discussion on geoengineering if people have comments to make.
All right, Kate, thank you very much for your inspiring talk. And then, of course, it triggers all the audience to ask questions and comments. But in this case, we have about 5 minutes to work on. So if you are storing your questions and comments for previous 4 speakers as well as Kate's talk, we will make a mixture of those questions and comments, okay? So please.
I'd like to ask Kate about this climate engineering. So thank you very much for your very interesting talk, of course. And I looked at this chart. You demonstrated what kind of solution can be used just for this engineering. But any engineering takes time, because just if we do this forest engineering for the forest, it needs some time to just to grow up. Mm-hmm. Do we really have time for this engineering, having in mind probably that we are very close to the point of non-return from the just for this development of CO2 or methane release. So actually, did you compare these characteristic time scales of all those engineering you demonstrated?
Yeah, that's a great question. So in the paper we did, and this is, as I was saying with solar radiation management, this is one reason why I think politicians and the public are very interested in it, despite the fact that scientists are against it, is because it could be a very rapid way to stop temperature. But the downside of that is that if something goes wrong, or if we stop doing it, we could have a very abrupt rise in temperature, because all of a sudden that shading would be gone. So that one would happen on a fast time scale, and it's really not recommended. But you're right, for forests to be regrown, that takes time. One of the things we discuss in the paper is stopping deforestation. So deforestation is actually a huge contributor to the CO2 problem, because the trees hold onto the carbon in the form of their tissue, their cells. And so when we start cutting down trees, then we're releasing that carbon back into the atmosphere. So I think Eric said in the comments in the chat section, he pointed out that that they are not, the geoengineering strategies are not really scalable, and there's a lot of uncertainty, which in terms of all of the different disciplines that we use to evaluate the different techniques, none of them was really found to be a perfect solution. Probably, abatement would be the best thing that we could be doing right now, but there's a huge economic cost that goes with that. And also the public doesn't want to give up its gasoline cars and coal-fired power plants. So we're making some progress, but not enough. So really what needs to happen is that the emissions need to stop. That's the primary thing. If we're going to do other strategies in concert with that, that might be another possibility, like with carbon sequestration and burial. If that technique can be perfected enough, then that might be a possibility. But if you have even 1% leakage per year, it basically makes it not a useful strategy anymore. You also have the issue of, if earthquakes happen, then that releases a very large amount of CO2 to the surrounding area, which can suffocate any living organisms. That happens naturally in certain areas. So I think they all come with a little bit of risk, but probably carbon capture and storage has the potential of helping us if we can perfect the technique.
Okay, thank you, Kate. Any other question or question?
I have a question. Kate, I really like your system thinking, picture thinking about geoengineering, how it affects from various aspects, ecology, economy, stakeholder, etc. I'm wondering if you've looked at it from a sort of an interference or interaction with the Earth's major system and cycles perspective. Because, how we got to the CO2 problem was because we know how to mess with the the fossil fuel and stuff, create all these energies, and then we mess up the cycles. Okay? Right. So if, this also would be a really good leading to my talk later, which is sort of from that consideration, how do we figure out what the solution could be? Can you expand on that? On the system of cycles?
Yeah, so in the paper we did, I actually worked quite a bit on this part. So there were two science people. Well, I was more looking at the ocean side, and then my colleague Daniela was the terrestrial person. And we did quite a bit of work looking at how the biology and the chemistry and the physics all interact when these different approaches are applied. And that was one of the things that went into our ranking for the technical potential and also the ecological risk. So we did consider those things, and just as an example for our ocean iron fertilization, it affects the carbon cycle, it affects the iron cycle, it affects the biogeography of phytoplankton, who grows where, how fast do they grow, and of course, since they're the base of the food web, that affects the entire food web all the way up. So those are just some examples of how the Earth system would respond to something like ocean iron fertilization. A lot of these techniques have ripple effects that are not necessarily obvious when you first start thinking about it, but a more thorough investigation into them reveals that they could have lasting consequences.
Okay, Kate, thank you for your comments, and also you guys, the audience, had a very interactive attitude, and also the dignity to cherish the presence, but on the other hand, living with the time. Thank you. So now we are 11:30 our time, and the Moscow time is 10:30 p.m. Thank you for your audience in this late evening, but still enthusiastically participating. And I button touch to Sasha to be the chair. Sasha?
Thank you, Toshe. We are moving to the second part of our forum. It will be mainly about nuclear energy. And I would like to give the floor to Professor Ning Li, New Paradigm for Civilian Nuclear Energy, Perspective from Energy Hierarchy and Fundamental Safety. Please.
Okay, thank you. Thank you very much. And thank you, Professor Tajima, for including me in this, informative and productive forum. So, I'm going to start by following on sort of what Katie just talked about, from these perspectives. How do we envision, how do we reach the solutions? Okay, so let me bring up my presentation. Now, before I start, I had, worked in the national labs on, amazingly, it was 20-some years ago, started on nuclear waste transmutation solutions. And then going on to Generation 4 nuclear energy system, advanced fuel cycle initiative and stuff. So by very fortunate circumstances, I was able to get into this sort of early renewal of the civilian nuclear energy in the United States and then around the world. And then by before 2008 or 2009, another set of fortunate circumstances set in. Bill Gates of the Microsoft fame, and collected people started to thinking about energy solutions to the climate problem. And I was very fortunate to be part of that. And so during that process, I was sort of stepping gradually away from the scientist approach of sort of observe and study, not interfere, to a more of engineering technologies, sort of a mode of actually trying to come up with solutions. And so this is my sort of a presentation of nearly 3 decades of work on nuclear energy. And also in the interim time, I also had the opportunity to work with many amazing entrepreneur investors in other part of the clean energy, like renewable energies and also energy storage, electric vehicle, etc. So here's a sort of a, we are switching gear a little bit toward the solution part of this session. Now, because once I started working with the developers, the entrepreneurs, investors, and looking at all these problems, time become immediate, obvious constraint on what we can do. Okay, so I don't need to go through the gigantic scope of the climate change and global energy, and also the opportunities it generates. But in this sort of a big picture, sort of a frame, where is nuclear energy? What can nuclear energy, do in a realistic time scale that really affects? Okay, I mean, if anything, today's preceding talks just only added to my urgency of this. I've heard people, talk about the permafrost melting and releasing of methane, and then the ice sheet melting. These only have not like 3 decades or 4 decades of time response time, just only a few years to 15 years of time. But having worked in the nuclear for such a long time and across many fields and applications, it started with a ban, I would say. In the 1950s and 60s, Atom for Peace, nuclear energy will become too cheap to meter, etc. And then 3 very catastrophic accidents happened: the 3 Mile Island, Chernobyl, and Fukushima, that really stopped the further growth and expansion of nuclear power. And so by 1996, the global share of nuclear electricity peaked at about 17.6%, and now it's dropped down to about 10%. So, as a practitioner myself, I've been dreaming for nuclear renaissance for 20-some years, and we are still kind of dreaming, although there are some signs of renewed development that's coming out in recent years, but we are far from getting there. Okay, I saw in the chat room that people were asking about the China's nuclear power development. Even that was the largest civilian nuclear program in the world and the fastest growing market, it still pales in comparison to other forms of clean energy and energy storage. I won't need to talk about fusion because, we will have a dedicated discussion on this, but fusion was also sort of a, people jokingly say fusion energy is always 30 years away. Okay, so how do we approach this? So one of the things that because I've had to step out of just study, observation and study, and do lots of development and investment. So I started thinking, do we continue to do more of the same? Or maybe we should think different. Okay, here's one of my favorite quotes of Einstein's, is we cannot solve our problems with the same level of thinking that created them. Okay? Like Kate said, lots of the problem that we developed was because we know how to deal with fossil fuels, deal with all these things. And our humans sort of innate urge just to do more created bigger and bigger problem as we do more and more of these things. So maybe it's time, given the state of all these accumulated knowledge and skills and capacities and advances, can we, think them from a fundamental and systematic point of view, and rethink the problem and rethink the solution. So my approach present here is to organize the solution thinking through the understanding of the primary energy hierarchies and achieve fundamental nuclear safety by the whole system engineering design taking into account the major system and cycles on Earth. If we, the climate change was a major imbalance because we did something to the system and cycles since the Industrial Revolution. So if we're going to solve that problem, reverse the trend, we have to start thinking at that level. So, this is sort of my key sort of insights and finding for this, and sort of a preview of the later part of my presentation. Is one is nuclear energy is truly unique from the primary energy hierarchy sort of a perspective. It is not part of the sort of our biologically relevant material cycles on Earth. Okay, all the nuclear elements, etc., exist kind of outside the biosphere and cycles that's biologically relevant. Okay? And then the other is artificial nuclear fission. It's also different from most other energy systems in that it's self-sustained and not driven system. Most of energy systems are driven in the sense of you add fuel, you stoke fire, or in the case of fusion, you drive with plasma confinement or injection of something. Nuclear and artificial nuclear energy, or what I call artificial nuclear fission, is self-sustained, it's not driven. Once you get started, you can't stop it. So the fundamental safety with sort of a new safety category and design principles can be achieved from robust fuel, meltdown-proof reactors, and differentiated design, which I will expand. So let's start with the sort of the primary energy hierarchy. Okay, so this is what a physicist view of the origins and transformation of all the primary energy on Earth. And we have the majority of it, over 90% of it, is nuclear origin. And of course, most of it is from the solar sun's fusion that comes cascade down to all the biomass, fossil fuel, thermal and photovoltaic, etc. And then coupled with a little few percentage contribution from the gravity, mostly the Earth's moon, we have some sort of a hydro, wind, and tidal portion of it. And the fission part, we've always kind of had the geothermal part, which is a part of the fission sort of thing on Earth. But what I call artificial fission, which is the traditional nuclear power, is what we are able to apply the science and technology and generate energy. Now, in this hierarchies, from the top and down, every time it goes down a level, the energy is drastically diluted. Okay, the density, the flux and stuff is diluted. And then it goes back up and concentrates. So the only thing that in the Earth, in the natural sort of form of primary energy, fossil fuel is naturally concentrated for us by the geothermal and chemical process. And this is the qualitative picture. Now, if we look at it more quantitatively, and I want to distill everything down to the most fundamental interactions forces, I'm using the electron volts of each unit, whether it's atom, nucleus, atom, or molecules, when they, what the energy barrier you have to overcome, and then what's the energy release, and what would be the thermal energy, whether the temperature it's working at, or the output as the system is operating at. So, on this scale, which is only, on the milli-electron volts to tens of electron volts, you can see fire is much higher than wind and hydro. Okay? And we got helped by nature because of the lightning, striking of stones, etc. That we were able to use fire as our primary energy before the Industrial Revolution. And then we discovered the use of fossil energy. The fossil energy, look at the scale, on the vertical scale, now it's 100 times. It's more than the previous one. And on this scale, chemical energy dominates, and those fire, wind, and hydro just sort of disappeared on the scale. And of course, we also had the solar energy, which is the largest growing energy in the last decade or so. It will be, from this year on, I think it's going to be the dominant new capacities of energy generation globally. And we also helped by the nature, because we're able to use fire and naturally existing sort of reactions preceding this sort of a seemingly more difficult form of energy. And then you move forward a little bit, you look at nuclear. Now I have to increase the scale, the vertical scale, by 6, 7, 8 order of magnitude. And then all these things just disappear. Okay? This is dominated by nuclear fission and nuclear fusion. Okay? So that shows that, that the potential what nuclear can do, if we do use the energy from nuclear fission and nuclear fusion. Now I have to sort of use a logarithmic scale now to put everything together in one picture that you can see. Okay? And you can see the progression of the difficulties of using them and also the potential of using them. Okay, and now in the case of nuclear fission, we were also helped by the nature that the nuclear synthesis that happened in the cosmos that gave us a lot of the neutrons that are not stable. So you can actually make nuclear fissions self-initiated, self-sustaining as compared to nuclear fusion. And the difficulty, of course, and not just the difficulty, the reality is we cannot exceed currently for the foreseeable future, the bond strength of materials is in this band, Okay, so we have to know what our constraints are. And this is the constraint that we cannot escape from. But you can see nuclear, with the barrier we can overcome, the energy is so large, but the working condition is possible under this. Okay, now fission is very different. Fission have to solve a whole different set of problems. Fusion. So we've all had this sort of urgency discussion before, and here is again using that energy sort of a thing. Look at just biological life, sort of metabolism, and lifespan. Okay, they are sort of determined by the Arrhenius equations through this activation energy, and 2 degree increase of average temperature on the surface of the Earth would increase the metabolism by about 20% and will shorten the lifespan by 20 to 30%. This is sort of a drastic change that biological evolution just cannot adapt to. And this is not just sort of happening on sort of these particular thing. If you look at, one of my sort of favorite physicists in a book about, how the social and city development that's happening, they are all accelerating at sort of a super exponential scale. So we are basically having a compounding problem, and the problem coming at us is bigger and faster. So how do we apply this sort of a thinking and the constraint to our nuclear problem? So now understanding the primary energy hierarchy and having sort of a view of the cycles, we now understand the artificial nuclear energy can only be utilized through heat. Okay? And it's not a driven system. Okay? They are not driven. We need to control them at criticality. And this is different from any other system, which will change to a wholesale changes in the safety categories, in the design principles, and how we build and operate the systems. So by fundamental safety, I'm talking about the typical reactor safety, but also expanded to include ecological, environmental safety, economic, regulatory, investment safety, and non-proliferation nuclear material safety. And this will lead to a set of things we need to be doing. Okay. Now, it looks like a daunting challenge that how do you do all this stuff and in the short amount of time that's available? Well, if we go back again to the basics, we may be able to have an understanding how we can do these things, and then without bringing or minimize unintended or unknown consequences. Okay, one of the things is if you look at the major systems and materials, all the previous 6 presentations in some ways talk about, you know, the systems we are in and the cycles, whether it's carbon, oxygen, water, nitrogen, phosphorus. And these cycles, if they are driven by external energy, can be sustainable. It has been sustainable on Earth for billions of years. Okay? And also because we are part of the system, using that system to generate energy is the most familiar approach to us. So we do a lot of it. And that got us into the trouble. Okay? So one is we are able to scale them up very quickly. And of course, once we scale them very quickly, we also cause us all these problems. And these problems are inherent in all these fossil fuels, but also in many of the renewable energy systems that are in them. They embedded in because we are changing the system and cycles. The nuclear materials energy, however, is managed from the beginning to the end, and that's separate. The material and energy is separate from the biological system, okay? But this also gives us the severe disadvantage because unlike the fossil fuels energy, lots of people know and how to do it. You know, you look at that coal presentations picture, these things are miles and miles big, you know, open pit mining and all these things because people know how to do them. Nuclear is limited in that perspective. So the advantage of it, not in the major cycles and systems, is also a disadvantage of doing them. So we have to somehow bring in this use of nuclear energy sort of through some accelerated approach that minimizes this barrier. Okay? Now, one of the barriers is how we think about nuclear energy. For over 6-7 decades, we thought, based on the early understanding and presumptions, is the fissile elements were very rare. We need a fast reactor with high breeding ratio to meet growing energy needs. But the MIT study for the future of nuclear fuel cycle in 2011 pointed out these assumptions are outdated and mistaken. Okay? And so, you know, if we are working on the outdated and mistaken assumptions, presumptions, the more we do, the more trouble we got into. And we just can't move it, as evidenced by nearly 3 decades of stagnation or decline of global nuclear energy. So you look at, you know, these assumptions, what I call a cosmic sort of energy cycle, is thorium and uranium, uranium is a predominant fissile material for nuclear power, is really, really abundant. Okay? We have 40 trillion tons of uranium in Earth's crust, 4 billion tons in seawater, which is kept in equilibrium with the rocks. And then we only use 8 to 9 million tons per year, okay, globally right now. And the price per energy output is less than 1/100th of the price of natural gas, okay? So, you know, we were designing an operating system based on sort of a totally different reality of the availability and the cost of these resources. So
5 minutes more.
Yeah, okay. So the increasing safety requirements led to degrading economies and you know, the flexibility of deployment that lead to the lack of fundamental economic, regulatory, investment safety. And the current technologies often added the complexity and cost. So making it lack of fundamental assets, evolution, ecological, environmental, and regulatory safety. Okay, mainstream reactor designs, well, they were adapted from the early military uses, so they lack of the fundamental non-proliferation nuclear materials. So on the one hand, we want to do more clean energy, low carbon energy, but on the other hand, we have many headwinds that are opposing its growth and expansion. And so, in one picture, I can show that because of how we approach to the design of construction and operation of the system, is we added layers and layers of safety emergency system without fundamentally eliminating sort of the problem of nuclear power. And the tracing the source is the power density of the fuel is too high, the radioactivity leakage barriers are not high enough, and the reactor design have too much power and too high a power density. And not only they are only suitable for large base load powering large grids, you can hardly build them in less than a decade or two's time. Okay, so you cannot do much about nuclear energy, and so this is why it's sort of a lagging behind. So, you step back with the understanding of the uranium resources, and then ask, why do we use nuclear power? Okay, we use electricity, use heat, use propulsion, and of course, it obviously needs to be the ease and safety of ownership and investment, etc. And now, in this context, we are also talking about mitigate climate change, and we have to scale up the deployment in time. Otherwise, it becomes sort of a, less of a contributor. So, I don't have the time to go into how these things would derive, because we are also developing and investing in these. So this is what's built from the ground up, and we sort of reached the sort of more abstract level, these main points. The one is we need the robust fuel and the meltdown-proof reactors, and also differentiated design. Okay? And so the safety-based design principles have to be rethought, because the nuclear energy system is so different from the other. I saw an earlier presentation about effective power density of nuclear, which is actually lower than natural gas by his calculation. It's still the missing element that's considered there is nuclear power density, although it looks low, the energy density is 100,000 times higher, 10,000 to 100,000 times. So when nuclear reactor stops, it's not a stopped system, it's still an energy system. So we have to reconsider how we design the systems by considering the shutdown conditions and then the operating conditions. Okay, then pick the level that's suitable to use. Okay, so that will lead to a very different change of nuclear reactor. And then we can redefine the safety levels from the fundamental safety, which is no fuel damage, no reactivity leak, to sort of a radioactivity safety. Okay, reactor can be damaged, but fuel is not damaged. To the probabilistic safety, which is what the currently adapted. Okay, there's a small probability of those things happening, and that sort of give us sort of in a schematic way that how we should, instead of making the reactor more compact, higher energy and total power, we should relax so that the other consequences are reduced. Okay, so there's an optimization that's going on with this approach. And the differentiated sort of design. You look at these, what I show here in the pictures, is all these similar technologies, one for different purposes. You design them differently, and sometimes with the opposite design objectives. But the nuclear reactor was, the main nuclear reactors were a sort of a more direct adaptation from the early military uses, and we've never really veered far from it. And so new nuclear would have to be somewhat different from it. Okay? So to summarize, I think the nuclear energy suffers from these challenges: rising costs, safety concerns, and very limited markets. And the convention problems typically creates cost and safety dilemma. And of course, there's also the safety, security, and non-proliferation. And those are post-design add-ons. So they always add to the complexity and cost. And I proposed, and we are in practice doing these, is to rethink the safety goal and design principles, and then basically get into the nuclear 2.0 fundamentally safe and manufactured system. You know, I will conclude here, just sort of recalling a conversation I had when I was advising Bill Gates, and we had, you know, sit down talks with the leading nuclear executives, and he kind of half jokingly saying, you know, I don't understand the Gen 3, Gen 4 nuclear energies. It's making the same output. It's just more costly and more more layers of system. How do you survive in a technological world, which, well, it wouldn't, okay? So there's something fundamentally that can be improved and needed for the civilian nuclear energy. And here's a way that we proposed how to approach. So with that, I will, and also this thing on the left here, Doomed to Cooperate, is written, edited by my mentor and good friend, Dr. Siegfried Hacker, who is probably quite well known in Russia. And this is a picture of Dr. Hacker shaking hands with the father of the Soviet atomic bomb. And the title of the Doomed to Cooperate is also very relevant for our today's discussion with the climate change that we are doomed to cooperate. Thank you very much.
Thank you very much, Ning. Unfortunately, we don't have time for questions. So if there are questions, please put them in the chat. And I would like to invite the next speaker, who will be Professor Stepan Kalmykov from Moscow State University. He will speak about novel strategy for nuclear energy generation. Please, Stepan.
Thank you very much, Academician Sergey. So I need to share the screen, but I cannot do it before the previous presentation is on. So, Professor Lee, can you switch off the presentation?
Yeah. Okay. Yeah, I've switched off.
So, trying to find the, okay, here it is.
Okay, good. Mm-hmm.
Can you see my presentation?
Yes.
Okay. So first of all, I would like to thank Professor Tajima and Academician Sergey to letting me speak here at this forum on climate change and global energy issues. As a nuclear chemist, I would like to continue my presentation with the nuclear energy as one of the energy in the pool of different energy sources and how it can help to solve the global change of the zero emission. So I represent Moscow State University and Russian Academy of Sciences in Frumkin Institute of Physical Chemistry and Electrical Chemistry. So first of all, we need to define where are we now and what is the goal and how to reach this goal. So one of the aims that is on the slide is decarbonization target of 30 grams of carbon dioxide per kilowatt that was formulated by the OECD. And certainly the nuclear energy is one of the concentrated source of energy, and green sources of energy can be used to solve this, to reach this aim. I don't want to go deep into some introduction of the nuclear science and nuclear energy, as Professor Lee already did it, but I would like to stop on the few more basic things. So first of all is I would like to mention that an increased share of low carbon sources, as well as drastically reduced level of fossil fuels, work together in harmony to secure a reliable, affordable, and clean future energy consumption. This will require a large increase of all low carbon energy sources, of which nuclear is an important part. So here, the forecast of the electricity consumption growth in low carbon scenario is presented. So the question is, what would include this low carbon scenario? What would be the energy sources in the future? So according to one of the forecasts, the share of fossil fuels would decrease, as you can see it in the image in the lower part of the slide. At the same time, we have the increase, a large increase of the solar, wind, and nuclear energy. That is one of the major concentrated sources of energy with zero emission. And certainly the zero emission could be proved on the slide here as well. On the image, you can see that emission of nuclear is even less than the solar, biomass, and incomparably low compared with the coal and gas emissions. Provisions of the clean and reliable energy and reduction of the air pollution. So there are two numbers are presented here. One is the forecast of the OECD International Energy Agency saying that decarbonization scenario, electricity generation from nuclear sources increases by almost 55% by the year 2040 to 4,300 terawatts hour, and capacity grows to close to 600 gigawatts of electrical power. According to the World Nuclear Association, the Harmony program proposes the addition of 1,000 gigawatts of electric power of new nuclear capacity by year 2050 to provide 25% of electricity from 1,200 gigawatts of electrical power of capacity. So, and this is reliable numbers that could be reached, because even in year 1940, 84, 31 gigawatts of electrical power in nuclear energy was added by a single year. So this is where we are now. So this is the world nuclear power generation. As you can see, this is quite amazing, but Chernobyl accident, you can see the point here, it does not really affect greatly, it even doesn't affect at all the increase of the share of the nuclear generation worldwide. And the decrease due to Fukushima accident and in the year 2011, we can see it here, it's not really dramatic. And in few years, we get back to the same numbers that were reached in the year 2010 before the Fukushima accident. So this is just basic numbers where we are again now. The first commercial nuclear power stations started in operation in the 50s. The first commercial nuclear reactor in Eurasia was launched in 1954 in Soviet Union in Obninsk. So all the technologies that were used at the early days for in the weapon programs, they were used also for commercial nuclear power stations. Nuclear energy now is about 10% of the world's electricity from about 440 power reactors. Nuclear is the world's second largest source of carbon-free energy sources. So it's about 29% in year 2018. And now it's about 50 countries somehow utilize nuclear energy in about also 220 research reactors. More than 50 new reactors are under construction, and you can see there's the share of nuclear through the different years. and you can see that there's a relatively large increase in the share of nuclear for Asia. This is few slides with the world map showing, the first one is showing the change that we observed in year 2019 for the annual discharge in fossil fuel consumptions. You can see there's a large increase in China with large decrease, but smaller than increase in China, decrease in United States, and some smaller decrease in Russia. But the truth is that in China, if we go further, the low carbon energy generation is also increased in China. So this is the country that has dramatically increased the energy demand, and both from different sources, from fossil sources, from low carbon, and also from nuclear. As you can see in China, the addition is 130 terawatts hour compared with only 9 in Russia and minus 1.7 terawatts per hour in United States. Before going more into the details of this new strategy for nuclear energy generation, some more basic but very important facts. So according to the IEA World's Energy Outlook, the cost of electricity in China from onshore wind, solar panels, and offshore wind is respectively 60, 50, and 140 higher than that from the nuclear. So means that in terms of the economy, nuclear is preferably compared with wind and solar sources of energy. According to OECD, Nuclear Energy Agency, a mix relying primarily on nuclear is the most cost-effective option to achieve decarbonization target of 50 grams of carbon dioxide per kilowatt of power. Important thing that the average dose rate for the population living near coal power plant is about 40% higher than for the populations living in the near nuclear power plant. Certainly, I consider only non-accidental operation of the nuclear power plants. Raw material base, uranium is only 5% of the net cost of the nuclear power generation, compared to about 75% of the crude oil and gas in the fossil fuel energy generation. So it means that these markets are much more volatile and they dependent on the global prices on the fossil fuels. So this is just an example. The particles, why the population living close to the coal plants, they get higher dose rates. So one of the excellent examples coming from the Rod Ewing, who's actually foreign member of Russian Academy of Sciences. So they detected the particles in Detroit in coal plant of carbonaceous matter similar to fullerenes, and nanocrystals of uranium dioxide was embedded inside the structure of this fullerenes. Means that they can be easily transported to the air through the large territories and population living near these coal plants. They breathe this air, and this affects the lungs, and this affects the dose rates of the people living near coal plants. So what is the problems associated with nuclear generations, and the problems where chemists, physicists, engineers should solve? Certainly the social barrier, the reactor safety issues are very important, and the safety of spent nuclear fuel and radioactive waste management programs. This is really large social and public acceptance problem. Nuclear security and non-proliferation, the issue that we cannot escape. So this is very important. Technological infrastructure and waste management, and certainly the option for geological disposal. the option between the closed nuclear fuel cycle, where we have the reprocessing, and open nuclear fuel cycle, where we have the one-through option of the spent nuclear fuel. So this is just an example, considering the geological disposal. There is no single license deep geological disposal in the world, just because we need the forecast, we need the safety assessment in the years of 10 to 6 or even more. So you can see this is the toxicity of the spent nuclear fuel and different contributors of the contributors to this toxicity. You can see why Russia and many other countries, they go to the closed nuclear fuel cycle, where we have the radiochemical technologies to separate different fractions, different radionuclides from the nuclear fuel cycle. You can see how the picture is changing when we separate plutonium isotopes. Here, this is how it changed when we separate americium isotopes, and here how it looks like when we got off neptunium isotopes. So it's only iodine 129 and technetium 99 that is responsible for long-term radiotoxicity. And this radiotoxicity is lower than the radiotoxicity of uranium ores that start to be much more easy to license and much more easy to for the safety assessment. The main problem with the nuclear generation, with the nuclear energy, is the nuclear waste. So the nuclear waste that originated on all stages of the nuclear fuel cycle, and especially upon the reprocessing of the spent nuclear fuel in the closed nuclear fuel cycle. So this is just the numbers. But I would like to mention here that you can see the activity is very large, both liquid and solid. And you can see that if we consider volume, so the volume is mostly low level and intermediate level waste. High level waste is not that much in terms of the volume and the weight, but it corresponds to more than 99% of the activity. It is demonstrated here. We can see that liquid or solid waste, low level, is 99% in terms of the volume, but it's only, for example, 0.009 and 0.003% in terms of the activity, and vice versa for high-level waste. The volume is not very large, but the radioactivity, it's dominating. It's about 99%. So the main technological challenge is what to do with all this waste, how to treat them, and how to safely isolate them from the humans. So one of the possibilities, the closing of the nuclear fuel cycle of the new generation, where we use both thermal neutron reaction and fast neutron reaction. This is the way how we are planning to do in Russia. So this is the image of the open nuclear fuel cycle. So we have uranium mining and milling, then we have isotope enrichment and fabrication, then we have fuel that goes to the nuclear power plants with thermal neutron reactions. Then we have the spent nuclear fuel and the storage. And probably in the future, when some deep geological disposal of the spent nuclear fuel will be licensed, so all this spent nuclear fuel would go to the deep geological disposal. This is how the classical closed nuclear fuel cycle looks like. So after the storage, we have the reprocessing. So we separate uranium from the spent nuclear fuel. We regenerate the fuel. It goes back to the nuclear power plants with the thermal neutrons. The problem is that we have a large volume of various radioactive wastes that are originated at the reprocessing step. This is how the closed nuclear fuel cycle with both thermal and fast reactors looks like. So it is already realized in Russia. So uranium, again, is reprocessed. It goes to the reactors with the thermal neutrons. Plutonium goes to the mixed oxide or mixed nitride fuel production. It's already launched in Krasnoyarsk chemical and mining combine, and there is the experience in fast neutron reactor operation at Beloyarsk nuclear power plant. So there is the two fast neutron reactors that are under operation at this nuclear power plant. So the mixed oxides utilizing plutonium originated from the reprocessing and uranium could be used at this type of the reactors. And this is how it would look like, I hope, in the future. So this light blue arrows corresponds to the project that we have to create. So some new reprocessing technologies would be tested, and uranium and plutonium would be also given, placed back to the mixed oxide or nitride fuel production for the fast neutron reaction. The major thing is that we would separate the minor actinides and mostly americium and neptunium for burnup. So it would be transmutation using either molten salt reactors or using heterogeneous reactor, and then geological disposal for high-level waste that have the half-life period of about 30 years. So the new strategy based on the nitride fuel, so I'm not going deep into the details, but the properties of mixed nitride fuels is to, for example, the density is better than compared with the metallic or oxide fuels. So in this fast reactors, the dense nitride fuels are proposed as a nuclear fuel. The main challenge for the chemists, the main challenge for the radiochemical technology is that the fuel after these fast reactors would be fuels with the relatively higher burnup. Let's say about 2 times higher burnup compared with the thermal spent nuclear fuel. We expect that would be lower exposure time. So it means that the spent nuclear fuel would be much more hot in terms of the radioactivity compared with the spent nuclear fuel from thermal reactors. High fission product content, so macro concentration of different fission products, and high plutonium content compared with the thermal reactors. This is the principal scheme that combines the two techniques: the pyroelectrochemistry on the head operations, where we have the very high radioactivity of the spent fuel, where we cannot use wet chemistry techniques. But after pyroelectrochemistry, we can do hydrometeorology to separate, to fractionate different components of radioactive waste depending on the half-life period, and reprocess plutonium and uranium, as I already mentioned. One of the challenging things is that we have is the separation of the elements that have very similar properties, like americium, that is a half-life period of 400 years with relatively short-lived europium and curium. So again, if we separate americium from the waste, we transmute them to relatively low half-life period fission products. We can go from the tens and hundreds of thousand years of safety to hundreds of years. So as you can see it in the image, so it means that we solve together the ecological, environmental, and also economical problems. So how we do that is that traditional techniques that we used. So based on solvent extraction, the separation factor is very low. So we need a lot of settler mixer extraction units, like 100, 150, to meet all the non-proliferation requirements. Means 99.9% of the yield for the fissile americium. So that also results in the large volume of secondary wastes. So what we do here is that we try to use different new novel extraction systems. So we start with the quantum chemical calculation for different molecules, I think hundreds, thousands of different molecules, And using DFT calculations, we try to figure out, let's say, tens of the molecules that possess appropriate properties. So selectivity, efficiency towards americium separation, stability in different media, etc. Then we do synthesis. So by DFT calculations on the supercomputers, we minimize the practical experimental work, synthesis and extraction. So we synthesize only few ligands. Then we make tracer experiments in the lab. We certainly test the radiation damage and radiation stability of these molecules. Then we do large quantities, large amount batch tests with the milligram quantities of rare earth elements, americium and curium, to see if everything is work at the same level as the tracer in the tracer experiments. Then we do experiments with
5 more minutes.
Yes, I'm almost done. Then we do technology development based on the real technological schemes at the different facilities for reprocessing. And by combining this data, we also can do deep learning. So we can have the global viewpoint of the metal complexation, database on development, predictions of the molecule properties, etc. So this is just an example of the different molecules. So there are hundreds of them, but in practice we do about maybe 10 of them. So we predict delta G. That means that the selectivity of one element like americium within the mixture of rare earth elements and curium. There is a lot of ligand design that we can do. For example, here, so this molecule, the first molecule, is quite it's not hard. So it can be moved, and we need some energy to pre-organize this molecule compared with this one. So this model is have a hard structure, means that the energy to produce the complex with americium is lower. So this molecule is much more efficient compared with the previous one. So we do also some predictions of radiation stability, how the molecules will disintegrate, and this really can be predicted, and it's well tested in the practical tests by electrospray ionization mass spec to detect radiolysis products. And by stepwise molecular design, we can go to the very selective molecules that can give us the selectivity factor of 6 compared with 1.5 with the classical TBP, for example, with a high radiation stability and relatively high solubility in technological solvents. As a result, we can separate americium with a purity of 99.9% on the yield of 99.9% that fits the non-proliferation requirements. It could be done in only 10 extraction units, 10 rinsing steps, and 3 stripping steps. So we minimize the number of steps, we minimize the number of secondary volume, and we can quantitatively separate americium with a high purity. To conclude, I would like to say that nuclear energy is the best or even the only option for practical decarbonization target of 50 grams of carbon dioxide per kilowatt hour of energy. Nuclear waste is the major challenges in the development of safe and reliable nuclear energy. New strategy based on the combination of thermal neutron reactant with cheap energy generation, with fast neutron reaction for recycling of fissile materials and burn up of long-lived radionuclides from waste. This is a new strategy, and I showed you that we are ready to launch it with, for example, with transmutation of long-lived americium isotope. So this would give us the decrease of uranium mining. This is also economic and environmental issues that are solved. This could minimize or eliminate deep geological disposal with saving only near surface repositories for the short-lived radionuclides. This is a cheap energy production. This is the possibility to use of excess plutonium that is also referred to non-proliferation issues, and this is very important. So by this, I would like to end, and thank you for your attention.
Thank you very much, Stepan. We have time probably for one question. So is somebody willing to put a question to Stepan? maybe me. Stepan, could you tell what is now the state of the art in developing of this technology in different countries? Probably Russia goes just its own way. What about China or other countries? And,
well, China is really would be, I think, #1 in the share of nuclear in the next maybe not 5 but maybe 7 years. So it would be #1 in the share of nuclear in the national electricity production. The interesting thing that at least 2 countries that, according to my knowledge, that is China and India, develops thorium nuclear fuel cycle. So as is already mentioned by Professor Lee, the content of thorium is higher compared with content of uranium in the Earth crust. And this is like a new ocean of possibilities for the nuclear energy generation if we also consider thorium nuclear energy production. We also can solve the non-proliferation issues because transuranium elements like plutonium are not formed at the thorium nuclear fuel cycle. So I think this is one of the future possibilities. At least 2 countries, India and China, have the projects in the thorium nuclear energy. So I think we're #1 in terms of the fast neutron reactors. As the France, they had 2 fast reactors, but they were shut down. But we have very successful experience in terms of the exploration of BN 400 and BN 600 at Beloyarsk and NPP.
so thank you very much for your very interesting talk.
So can I ask a question?
Yeah, one more question, please, Valery.
Can I ask a question?
Yes, please.
Yeah, you didn't speak about accelerator-based technologies of transmutation and also breeder reactors. Do you have any opinion about these, directions?
Well, for indeed, one of the options is the accelerator-driven transmutation. It's a little bit costly compared with the breeder reactors. So the 2 options are considered now based on the economy is the heterogeneous reactor, that would be a molten salt reactor that could be that could work permanently. So the fission products after the transmutation, for example, of americium, they could be separated online through pumping of the fluoride melt through some sorbents. And another possibility is to use heterogeneous reactors. So again, I would repeat that the economy of reactor-based transmutation is much better, it's much preferable compared with the transmutation using accelerated techniques.
Thank you. So thank you, Stepan, and we are now coming to the next talk, which will be given by Michael Binderbauer from Tri-Alpha Energy, and it will be about fusion energy solutions. So Michael, are you here?
Yeah, I am, and I hope you guys can hear me. And I just shared the screen. Is it visible? Let me go see if I can make this full page. Does it show everybody now the full screen? Good. So thank you very much for inviting me. And as you know, of course, we are connected through Toshi, and I've been following along the evolution from discussion to putting this forum together. And it's a great honor to be here and share some of the work we're doing. This is not a survey talk. This is more a talk about the work that we've been doing for the past 20 years. And as it relates to hopefully attacking things sooner than later. And as you know, when people talk about fusion, they always think 30 years. So I wanted to emphasize the idea of fast track, although I have to admit, as I just said, we're working on it for 20 years already. We're looking at a quite different way of doing that. And I wanted to introduce that. And this is maybe not as technical as some of the other presentations were, but I think it's sort of hopefully stimulating. And I mean, happy to expand in the written version with something that is more, technical in nature for the paper. But let me say first, this was a book that came out about 2 years ago now, I think it was. And in fact, I was listening to it in the car driving. I don't have time these days anymore to read things much other than the things that connect to what we do. And, he said, which almost made me lose my steering, said, we really need to clean up, we need to find a solution for clean energy and a switch to electric cars, some of the primary sources, of course, of carbon emissions in the world today. And it so happens that we're actually working by serendipity mainly on clean energy, but as you will see at the very end, I'll talk a little bit about what we're doing in the space of electric drivetrain and power management, power electronic solutions. So let me start talking a little bit, just very briefly, because I know most people covered this, just a slide on sort of the way we look at the future energy demand and what that tells us in terms of what kind of solution we're looking for. We've been thinking hard about this problem from day one, and this credit goes mostly to my PhD mentor back in the early 90s, late 80s, Norman Rostocker, who probably quite a few of you know. And Norman was obviously as much an insider in the development of fusion technology and plasma physics, as he was also critically looking at the end game and said the tokamak work, the stellarators, and the various others concepts may not be the best solution in the end when you look towards an applied end product in the utility space. And so this is what drove him and engaged me as a young PhD student back in 89 to begin working on this. And what started, frankly, as a thesis project evolved into now the largest privately funded fusion company. We're around for 20 years with about 250 people working for us. We have spent about $750 million, so $750 million in capital on this. It's become a much larger journey than I ever imagined it would be, but it's quite far along. And so I want to take you a little bit on a journey and share this with you, and then just give you a sense for what we've done. Talk a little bit about some of the benefits that come as byproducts as you work on developing cutting edge technology. So to me, the way I look at this going forward, and these data sets are all more or less similar, right? We're looking at a doubling of the electricity demand out into the mid-century. We know that is in fact coming mostly from an increase in rising standards in the developing world. You can see here global population increases by about 20% or so. And so this, whether you look at electricity, like here, you look at total energy demand, those growth curves are about similar. And so we know that there's going to be a severe impact, in particular in the infrastructure starved part of the world, to bring electrification and meet the power demand. And so if you're looking at the sectors, I mean, electricity for electric use today makes up only a fraction of this. In fact, 70%, as most of you know, of course, this comes from transportation and a good major chunk from the industrial sector, smeltering, cement production, et cetera. And today in those areas, only about 6% is in the form of electric energy. But nonetheless, when you add all this up, it's clear that there's in the next couple of decades, there has to be a transformation. As we heard earlier today, I'm a big fan of Eric Regnault and the work that goes on in Earth system science at UC Irvine. Anywhere you look, whether it's the ice melt or you look at the methane problem in sort of the polar circum region, it all points to us getting to a very peculiar situation that needs to fix soon. And so, just as the last speaker just said, nuclear energy is the only really carbon-free baseload, as we now call it, dispatchable source of power. And so if you're looking at that, the world is going to narrow in a choice that, is trying to use renewables where they fit, but it's going to need a complement. And that complement, I believe firmly, is going to be either fusion or fission or a combination of the two. And as we talked about fission a little bit, fusion doesn't suffer the long-lived radioisotope waste, et cetera, but it's got its other demons. It doesn't work today. So let me with that then switch and talk a little bit about what we're doing here and why I think fusion power makes sense. So first of all, if you look at criteria, what sustainable clean energy would look like in the context of the environment and the future growth of population. Ideally, we would want something that allows us the power to be made near the production center. So if you look at the world's urbanification, for instance, right, we have megacities now. Mostly they're along the coastlines. Some are very grown in a very organic, non-organized way when you think in some of the third world megacities. But in any case, while COVID maybe put a damper on people congregating, but in the long run, I think those trends are going to continue. And so if you think about power, the most efficient way without transmission line and stuff, you make it right where you need it. And that means you need to have a certain safety margin built in. And that also then starts to exclude some of the renewables because those don't necessarily get their energy there. I mean, the wind may not blow where LA is, although we have sunshine here, but you know, those kinds of things. Land use, clearly with more people and agricultural needs, et cetera, and the impact on the environment, just from a physical perspective, with transmission lines all over, vast areas covered by solar and wind, which obviously because of low energy density will need that footprint. Those are not ideal solutions either. As I said, transmission lines are a big thing. They are wasteful. They require space. They leave a big footprint in cost. So we want to minimize that. Clearly carbon free. If we can do this carbon free and we can be free of long-lived nuclear waste, transmutation is certainly one way to try to get out of that jail card free. But on the other hand, fusion perhaps has something to offer here that does inherently not have short-lived waste. And then likely, of course, lastly, if we think about mining and the operations to get the fuels we're burning, reducing the impact on those natural resources in the ground and on the environment is also important. So looking a little bit more granular here, right? So in the case of fusion, of course, that exists in form of dispatchable power. It's reliable. It has, however, the long-lived demons of the radioactive waste. And of course, as we've seen in some of the nuclear accidents, there's a lot of potential for disaster when it runs away. And the problem is that the public today, I believe, when we look at this from an end product that we try to get into the utility sector and we need public acceptance, the public is very averse today. Certainly in the United States, I can say this loudly. This doesn't mean me, but it means the mass relatively uneducated that's seen a Fukushima or seen, you know, a Chernobyl or something of that type and says, I don't want this in my backyard. Now, of course, gas and coal have supply issues, the variability in pricing. California is a great example. About 2 decades ago, when energy trading brought the state almost to bankruptcy. Those are big things, in addition, of course, to the carbon output. And then when you look at wind and solar, again, it's not quite affine to being put near the urban centers, and the variability is a problem as well. From a footprint perspective, we all know this, fusion is the highest energy density fuel. So if you look at this from a simplistic picture of what does it take to deploy a gigawatt of fusion power, well, you need less than a square mile of space, and you're many hundred times that in terms of a wind farm. And when you're looking at this from the perspective of what we're up against, right, today we're looking at a world, and if you talk to the people in the financial sector, they're all gung-ho on the reduction in solar prices and the reduction in prices of windmills. But today that makes about 12%. 80% of our power still comes in the form of fossil fuels, globally speaking. And so there's some areas that are a little bit more advanced, but this is sort of the average. And if I look at a future where most of that gap is made up now by renewable and non-carbon emitting sources, that's a tall order to fulfill. And again, against other constraints, this is a sophisticated problem. Yeah, I already covered this sort of the transmission line ideas. If you look at the US, it's a great case study, right? You have urban centers along the 2 coastlines. You have vast amounts of the interior with a lot of wind, for instance, Texas and the Central Plains, but you got to bring that power out to the coasts, and that is inherently costly and has other environmental impacts. And so fusion could be something, particularly a safe kind of fusion with non-radioactive emissions, and you can really put close to those productions, to those consumption centers, and that would make a big difference. Footprint obvious, you know, in fusion is a zero spec. We're looking here, and I'll talk about this in a little bit. We're looking at hydrogen boron with a stronger focus and interest than deuterium tritium for reasons that'll become apparent in a second. But it's clear that that's the direction we have to take. And when you look at the long rift versus the safety issues, that's again where I think fusion has a huge leg up if we can make it work. We clean, of course, it can be very safe. It will become very sustainable. There's essentially infinite fuel available. We're particularly interested in hydrogen boron, and that really was motivated by looking at the impact of neutrons and deuterium tritium neutrons in particular to the lifetime of the plant, and then the impacts to cost, to maintainability, to safeguarding a proliferation substance, not to even speak about breeding it and, you know, releasing to the groundwater and so on. And so the idea here to look at aneutronic fusion is something when you really look without care at the moment on the difficulty of the physics, so you want to do that, then that would be the ideal solution if you can make it work. And so this was one of the reasons that drove us to say, since most of the world in fusion is working on deuterium tritium, why not look at hydrogen boron as an option? And if you look at that reaction, it's marvelous. It produces essentially helium as a byproduct. Now, of course, there are parasitic site reactions that will make small amounts of beryllium, for instance, but these are mostly very short-lived isotopes measured, with half-lives in the tens of days or so. And then ultimately, of course, there is no irradiation zone around a plant like that. So it can really fit in with the idea of near an urban center. The other thing about hydrogen boron that's interesting, of course, is there's a lot to go around. You need very little to begin off. I mean, if you're looking at the scale of for instance, combustion-based gas turbine today, you're looking at something like a 500 megawatt installation. For a few hundred pounds or kilos of fuel, you could supply that facility with all its fuel for a year. So if you look at an infrastructure place like rural India, for instance, or Africa, how would you bring fuel there? You don't have pipelines, you don't have railroads for coal, et cetera, et cetera. You could do a helicopter dump of this kind of fuel, right? So this is quite exciting. And then of course, it's ubiquitously distributed throughout the surface and in the crust and in the oceans. And today it's mostly used as a commodity product in laundry detergents and cleaning products and the like. And so there's no price volatility, there's no Saudi Arabia of boron, et cetera. It has all those geopolitical angles that cause us to get at war with each other also removed. So it's a quite interesting thing. What stands in its way, of course, is that it's inherently difficult to do, because you need, frankly, about the temperatures in the order of 3 billion degrees, or if you're looking in nuclear units, around 300, 320 keV. That's the total temperature in a system like that. And as you know, fusion is creeping up to the 10 keV point in tokamaks and what we're doing as well. And that's still a far cry of about a factor of 30 away where this would need to go. But when you look at it from a more holistic picture and you just don't focus only on the physics, which you have to, of course, but it's one aspect. And so again, to the holistic idea, begin with the end in mind. What would be an ideal reactor? Well, you want something that has technological readiness. So the aneutronic fuel takes out a lot of the materials challenges, little or no radioactivity, clean operational scenario, et cetera. So there's a long list I could list here, but these are some of the highlights. If you look in commercial viability, then you'll see this in a moment. We're thinking of a very compact machine. There is very little environmental impact. As I said, today, boron is mined by the metric ton. Either it gets out of seawater, or we have here very large deposits in the California deserts, for instance, where they just strip mine it off the surface. Maintenance is relatively straightforward. But of course, the physics. You need the high temperature. You need, therefore, an extremely efficient confinement, and you obviously need good stability. And so when we began thinking of this, we understood that those other two leaflets are in place, but the science is the hard kernel, and it's clearly where all the risk is. It's obviously the main risk in fusion today, but if you think about the deuterium-tritium fusion, by the time it meets success in ITER, for instance, or perhaps in a few other machines people are working on, public or private, even when you have deuterium-tritium burn with a Q or a net gain, greater than 1, you still need to manage the neutrons, the damage, the issues around proliferation, and all these other things I mentioned. So how can a private company get into this, right? I mean, first of all, when we looked at this, we said what private sector does well is efficiently deployment of capital. It wants to learn quickly. A beautiful thing in California is that we're not afraid to fail here. We have the Silicon Valley as a wonderful model. Fail fast is usually the synonym with which people think of things. And you want to try and error, and you want to develop things with lots of cycling opportunities so you can prototype, dismiss, go to the next thing. Partnership, clearly, as I said, we're about 250 people, but that's nothing. We have actually a very nice pool of talent globally now helping. There are traditional partners you would expect in the universities and the national lab. And in fact, our largest and most historically long and productive and deepest friendship is with the Butker lab in Novosibirsk, right? So we have a beautiful relationship there with their plasma physics and neutral beams people for decades now, developing and moving forward the state of the art on beams, and then as it plays into the work we do and the work that they do on these mirror traps, for instance. But we've also tapped the private sector in the US. So for instance, Google is a component here. We're doing a lot of AI and machine learning work where it turns out that a lot of the innovations happening in the IT space are just as useful and applicable in the area of what we do. So we've deployed a large, particularly in the last 7-8 years, effort on machine learning and AI. And this goes into two vectors that I think are interesting. One is obviously to drive the reactor through a feedback control system. So in other words, you look for instabilities, you look for patterns you don't like, you teach it to the AI or the machine learning system, and then they counterbalance that with changing magnetic fields or changing the fuel rate injection or something like that. But the other thing we learned, and that was in a way almost as exciting, was operational optimization. And what I mean by that is again, back to cycles of learning. If you have an unknown terrain to go into with hundreds of parameters on one of these fusion machines, how do you make efficient headway to go from what you know today into the unknown as efficiently as you can? And when you think about this as a private company, we're under the gun of the investors. They write us a large check, they demand results, and if we don't, we're gone. And so it becomes very quickly a necessity of life to figure out how you can be really fast and predict in a way, how long is it going to take you to get from A to B? You need around 500 experiments. How can you make that learning rate as efficient as possible? And there's an interesting paper we wrote with Google a few years ago in Scientific Reports, where we showed a very interesting paradigm for high dimensional, sophisticated data sets with gaps and so on, how you can apply optimization. And what we also learned, which was interesting, that the combination of machine learning and AI and human intelligence, it creates an exponentiating function of fast learning. So it's the intuition of the person that's sitting at the control panel, the physicist, the engineer, together with the machine that can do all the number crunching. And so we've been deploying that very, very successfully. As I said, neutronic fuel is a big deal because if you go into the depth of DT, you're dealing with long cycles of licensing patterns and things, whether it's the Nuclear Regulatory Commission in the US or say, for instance, ITER facing the French regulators. We know that those are very big delay components. And if you can avoid those to a degree, that'll help a lot. So not just is it good as an end product, but it's also on the way good to focus on it. As I said, private capital is a big deal. And then I'll come back to that at the end. There's now a whole bunch of spin-offs, just like when the space race happened and people were forced to develop esoteric new capabilities. Fusion drives you to innovate across a very large spectrum of technologies. So let me quickly cover what we do. So we work with a thing called an advanced beam-driven FRC core. So this is a very simple plasma topology, actually. It uses a solenoidal magnetic field. You can see there with these sort of blue coils here. And if you think about that being just a solenoidal field, say from left to right, when you inject enough of a current there, with plasma being a very good conductor, you can create its own magnetic field that superimposed creates a confining layer of closed field surfaces embedded in some mirror-like structure from the outside. And this is what we call in the field a high beta configuration. What that means is that this environment is dominated by the energy in the kinetic particles moving in the plasma, not as in tokamaks by the energy that's deployed and stored in the magnetic fields. That already tells you that it's going to be more efficient from a cost and an overall design perspective, because you can operate with lower fields, you need less sophisticated magnets, and you can do higher power density in the core, and so you can also shrink the system. So compact high power densities linked to that. It also allows you to work with aneutronic fuel for reasons that are perhaps a little too far afield here. This has to do with synchrotron radiation. And this kind of magnetic field has a very low field region in the center where most of the fuel peaks. And so you get less synchrotron radiation there. It also allows you to work with what we call large orbit particles. And so this was something that Norman brought in very early. And where that comes from is the idea that in accelerators, like CERN, for instance, we have very predictable capability to hold clouds of charged particles in magnetic topologies very efficiently. And in fusion, the typical lifetimes we're struggling with from an instability perspective, those are 10 to 100 microseconds or so for, magnetohydrodynamic instabilities, for instance. And so it turns out that in tokamaks, this has been very nicely verified. If you inject energy particles that have a very much larger footprint in terms of their orbit size, they sample phase average a lot of the perturbations, and they become, not to say immune, but much better behaved. And that sort of anchors this plasma. And so we're injecting here tangentially here neutral beams at high energy that creates an additional layer of co-streaming particles of high energy that kind of improves stability and transport. And it's a simple geometry. And finally, and this is important, if you have to exhaust energy out of the system one day, in tokamaks, the exhaust systems, or as we call them, diverters, are at a premium because they sit inside the magnetic cocoon. Here, you would actually have most of the emission products streaming out to the axial ends. And there you can have flaring magnetic fields, you use a large scale surface areas, so you can reduce heat loading on the wall, etc. And here's just some examples of particles here oscillating in these fields from simulations. So this is sort of what it looks like, what we have right now. This machine is about 2 double-decker buses in length. It produces fields up to about 3 kilogauss, which is sufficient here to get us up to temperatures of about 50, 60 million degrees, or somewhere in the neighborhood of 30 to 40 plus keV in total temperature. We're operating here also now, 33 to 4 keV in total temperature. We're also here operating at densities of about low to mid 10 to the 13 per cubic centimeter. So this is still about a factor of 5 or so less than where we need to go for a reactor, but it's in the reactor relevant regime already. And it works remarkably well. We actually make plasma in the 2 end zones. We shoot this together in the center. We create this sort of hollow football that's rotating there. It's held by its own and the applied magnetic fields from the outside. And then we tangentially feed beams. And if you want to understand first order stability, it's like a spinning top. It's sort of an anti-aligned magnetic top in here and wants to perhaps flip. But if you give it enough rotation, which you can control through torquing from the injection of the neutral beams on the edge, we can control the rotation and we can hold these things very nicely stable. And in fact, feedback is an interplay between injection, frictional dissipation of too much over rotation, and then magnetic controls that basically position the thing and sort of keep it like almost like on a rigid axle.
5 minutes more. 5
Yep,
minutes.
thank you. So this is the progression of machines we built. We started in 1998 as a private company, raised friends and family money, and then migrated up to more sophisticated machines. Today we're operating the machine Norman here. That's our current prototype that we're working with. And as I said, this is fully in the collisionless regime. That means the physics that controls the plasma, that controls the instabilities and the turbulent transport is very much the same as the physics that controls the reactor state. So we're feeling very confident and we can take this data and extrapolate forward. And we're now beginning construction of what I think is sort of our final must demonstrate machine, which is a machine we call Copernicus. We think we will have that operating sometime in the later 2023. And we think we will be able to show that we can get net energy on a device like that in the 24-25 timeframe. And then it becomes a process of developing a demonstration plan in the second half of the 20s, although we'll probably start work. We've actually started working, but really get going in parallel to Copernicus on the engineering of that. But the goal is by the late 20s to be ready to have a first sort of prototype machine running. And I think this is not fool's hope. There's still a lot of work. I don't want to sugarcoat this. There's a lot of risk, but we think can do this. Let me just give you here a very quick idea of how this, how we run. We store very efficiently energy inside of a very sophisticated power supply system. We run about typically 30 millisecond discharges on that. And these frankly are only limited by the energy storage. These are highly steady state configurations. They're very well, nicely tamed. We can ramp them up. You can see here plasma heating occurring. You can see field ramps. You see the fast ion accumulation as traced by the neutron rate. So we use today deuterium and deuterium and deuterium in the machine, or deuterium and hydrogen. And so there's some nice neutron tails that we can look at, and they'll give us a good idea. So this is a state that's quite different at tokamak. Here, everything is driven by most of the pressure of the particles is in fast ions with large orbits. It's a very high beta machine. Tokamaks operate like maybe 8% beta. We're more like 90+ % beta. And what's really beautiful, and we had predicted that, when you look at the leak rates and you look at the energy confinement time, it scales beautifully. And in fact, it's an older trace. We now go out to almost a keV in electron temperature, and it scales with the square of the temperature. So in other words, if you increase the temperature by 2, you get about 4 times the confinement performance. And this has to do with the accelerator physics that Norman and I expected to come in. And we've now clearly validated this across 3 machines. And we've done very sophisticated modeling with our academic friends in the US predominantly, and it all agrees. So this has a very good chance, we believe, to bootstrap us, not just to DT levels, which is about a factor of 2 or 3 beyond where we are today, but also higher up by another factor of 10 then to make perhaps PB11 workable. So this next machine is about a 10 keV machine, gets us roughly where ITER and the rest of the field is operating. By the way, though, not at tens of billion, but at $250 million capex. This is the beauty of this. So much more compact, quicker to build, quicker to iterate on, and hopefully something that will be able to give the world by the mid-20s to make a dent then into hopefully by the late decade and then into the 30s in terms of adoption of fusion. Let me just spend 1 minute here at the end on 2 topics that I think are interesting. The first one's on power management. So when we built Norman, we consume about 750 megawatts at peak power level to run the machine. And about the grid feed is about 2 to 3 megawatts. And so we had to figure out a buffering system that heretofore didn't exist that can, capacitively mostly store this power, release it reliably at these very high power flows into about 80,000 controlled parts. And so we developed a unique, think of it like an ant farm. Instead of moving a boulder with an elephant, you have 1 million ants, small modular power supplies. And when that worked beautifully, and today that runs with 100% uptime, the fusion device, we said, can we deploy that elsewhere? And in fact, it turns out when you miniaturize it to the 10 to 100 kilowatt level, it can beautifully work in transportation. It can work in grid storage and buffering, peak shaving, power load shifting, etc. And there's sort of a connected ecosystem that in the end has clean fusion, hopefully in its center, or some carbon-free form of power, maybe small-scale fission or something the like. And then and around it, you have other decarbonization impacts from spin-off technology. And we're in fact now commercializing this. We actually signed our first licensing deal with one of the largest providers of utility scale mini and microgrids in the US. We're also in talks with some of the large tier 1 auto suppliers. And I think you'll very quickly see some of this fusion-derived technology in these other sectors. I think it's a very nice story. And let me close with something even further from home. This is an idea that we developed together with our colleagues at Butker. And this was taking these incredibly powerful neutral beams as fuel injectors for fusion and repurpose them as compact epithermal neutron sources for a technique called BNCT. If you Google it up, you will find it's a very interesting thing. It's been around for decades. It's the idea you inject the drug that brings boron-10 into a cancer cell. You irradiate it with low energy neutrons. The neutron gets swallowed by the boron-10, creates a mini fission event with a destruction radius of about the size of a cell. So you can locally disturb cancer cells without disturbing the healthy cells around it. The handicap with this has been that to date, they only could do these sorts of things on nuclear reactors. With these accelerator sources now that are uniquely capable by chance, what we developed fits perfectly for the low energy application. You can be very narrow band neutron sources. They can be very highly efficient. I'm happy to report that as we speak, we're just installing the first clinical system at a brand new cancer center in China. We have under contract now in the spin-off company orders from Europe, out of the UK and in Italy. And we just signed our first large US participant in the form of the Mayo Clinic, which is one of the largest clinical systems in the United States. So here's a spin-off that one wouldn't necessarily associate with fusion, right? Where you can take these things and bring them over. And because you developed esoteric technology performance, support fusion, you suddenly have something that can make a transformative impact on the rest of the quality of life. So let me close here. I know this was a whirlwind. I hope you got at least a hint of the idea. Be happy to expand more and further dialogue, and we'll share more as we write this in a written form. Thank you very much.
Thank you very much, Michko, for this very interesting talk. Actually, I would like to ask some short question regarding this therapy stuff.
Yep.
As I understand, there is the main problem there is not just not only the neutron source, but you need actually some drugs to deliver boron to the patient in quite targeted manner.
Mm-hmm.
Did you solve this problem in the United States, or
Yeah, so this is a great question. So very quickly, I didn't have time in there to do this, but so today what's used is called boron phenylalanine. It's a very small molecule. It carries 1 boron per molecule. It's intravenously injected. It works through a larger amino acid uptake in cancer tissue. So in other words, it has higher metabolic rate. So if you infuse it into the body, it will preferentially uptake there. To your point, you're absolutely correct. You can get best today between 3 and 5 enhancement in terms of the uptake into a tumor cell versus a healthy cell. And that's just because of the metabolic rate. Now, it turns out with that already, you can do treatments, and they've done, and in fact, this very drug, together with Sumitomo-based accelerators, the the Japanese regulators, the Japanese FDA, last year, actually, in the spring, went from a stage 2 clinical trial to full approval. So in Japan, you can now, for head and neck cancers and glioblastomas soon, you can actually get treatments with this. So it works well enough. Yes, to your point, it has side effects. There is collateral damage. Now, to answer though the question on the drugs, so we actually developed over the last few years a spin-off in the pharma area working on this. And what we're doing, and this is actually beautiful, there's a lot of work in targeted chemotherapy. There's a lot of work in antibody technology, et cetera, right? And those are all looking to bring these toxic payloads into the body. And it turns out if you cleave those off and you create the chemical linker capability to the boron, which is inert to the body, it's an easier problem, it turns out. And we have, in fact, now in mice, in testing in our lab here in Santa Monica, almost 40-to-1 enrichment already. And this is using, in fact, cetuximab, which is a fairly standard used antibody that's out in various pharma products. So I think you will see, not immediately, I mean, by FDA clearance, but I think within the next 5 years, you will see a revolution. And we're on the forefront of that with our pharma development. New drugs that can do much better. They can load more boron in the tumor tissue, so you need less irradiation time, and it can be more precise. And I think there's a lot of other options. There's a whole host of cool stuff. With parties in Japan, we're working on passive targeting, where you can look at the vascularization of tumors with leaks. And if the molecules are small, they can leak through there, but they don't leak anywhere else. There's a lot of vectors to improve what we have. And I think this bears a lot of potential for people that today are basically sent home.
Thank you. Well, some more questions, please. No more questions. So, Mitchell, thank you very, very much for your.
Thank you for having us.
Interesting talk. And now we are moving to the next talk, which will be given by Alan Weeks. Alan, are you here?
I'm here. Ready to go.
Alan is Director General of ELI in Europe, and he will speak about sustainable research and operation of the extreme light infrastructure. Please, Alan.
Thank you for the invitation. Accommodation.
Gentlemen, excuse me. Александр Михайлович. Александр Михайлович.
Да, я слушаю вас.
Позвольте мне идти спать уже. У меня 4 часа утра, мне в 9 надо на следующее совещание. Можно?
So Zimher Ismagilov, he is in Kemerovo, and now it is 4 o'clock in the morning. Probably we can forgive.
Because at 9 in the morning, I have another meeting. You know.
Yeah, he's going. He's to...
I would like to say thank you very much to all participants. Please excuse me.
For the contribution. Thank you.
Okay. And, see you next time. Bye.
So, Alan, sorry, please.
No problem. Absolutely. And I want to thank Professor Tajima also for the invitation and the great collaboration he's helped us with Eli. And thanks really to everyone, everyone in Russia who is pushing, it's Wednesday now. And I'm mindful of the fact that it's already enough to listen through a lot of Zoom presentations, and to do it at midnight or 4 in the morning is even more challenging. So this invitation is maybe a double-edged sword, but I'll do my best to keep your interest for the next 25 minutes or so and move quickly through some topics. A lot of the science and these developments that we've heard, particularly in the last 3 talks, are very relevant to my talk, but I don't plan to cover those things. So I'm glad that you guys have all covered those bases, especially a lot of the things that Michael, you just presented. I'll give a brief introduction of the extreme light infrastructure. It's a new facility in Europe. We'll take a look at the facilities and I'll give a couple of examples, but really just a couple too, of some research that's relevant, and you'll see exactly the overlap with some of the research that's already been discussed. I won't go into great detail, but I'll give you the references if anyone would prefer to or like to go and dig a little bit deeper. And then what's very important as a trend generally in Europe, I think it's also true in the US, and I know from talking to colleagues in Russia as well, that this is becoming a bigger and bigger consideration. While we're doing a lot of fundamental science, we're doing it at large research infrastructures, oftentimes that happen to not be very sustainable in their operations. We're using lots of energy, and we tend to always, of course, prioritize performance and the science, and oftentimes didn't even give an eye towards or a look towards how to run these facilities in a sustainable way. There's been a trend over the last 10 years or so at the large scale research infrastructures in Europe to think about ways that we can operate the facilities more sustainably as well. So I'll just show a quick case study of what we're doing at Eli to that effect. So Eli is the world's largest and most advanced laser research infrastructure that's particularly intended for users. So there may be more powerful lasers that are used for mission-based purposes, like the NIF laser that's used for fusion, inertial fusion in California and others. But really, Eli is set up as a user facility. It's international. It's the first to be built in Central European states, and it's funded by the European Union's structural funds. which is a specific investment fund used for infrastructure that's been applied in this case for science. These are pan-European facilities, and it was really prompted by technological developments made back in the 80s by Gerard Moreau and Donald Strickland when they were developed a methodology for chirped pulse amplification. This really brought laser technology out of a plateau that it had reached in the early 80s in terms of intensity and the way that we could manage pulses. This, as you'll see, has led to a new generation of petawatt and multi-petawatt class lasers, which opens up whole new areas of research. That for those of you who are not familiar with lasers, you may be surprised at some of the capabilities and some of the developments that are moving in this field. So ELI is on the European roadmap. That means it's listed as one of the key research infrastructures in Europe. It's been there since 2006, and we began construction back in 2013. And it's really 3 different facilities, as I'll show you, that have been built. This is following on a trend in Europe generally towards supporting large scale and high power, high intensity laser research facilities. And right now, Europe is really leading the world in terms of the intensity of the number of facilities and the number of petawatt class lasers are really concentrated in Europe. So the ELI timeline is after the idea for ELI, which was actually, written on a napkin back in 2004. So by Gerard and a number of other scientists thinking about how to reach an exawatt laser at that time. That's the vision, and that still is a dream that we eventually hope to achieve someday. It set off a kind of a preparatory phase to look at the feasibility of building such a large scale laser in Europe, and that was funded by the European Union, and it later led to a kind of 3-country approach to build the facility. It was understood that it would simply be too much to build as one single facility at one time. There was not an investment concentration. But by using the European structural funds, the Czech Republic, Hungary, and Romania were able to parse out the laser laboratories and figure out a good way to create 3 complementary laboratories that cover a broad range of laser sources. So that construction has been going on now since 2013, as I said, and is now coming to a head. And we're already in the commissioning stage, and we have a number of lasers coming online, trying to get up to our design parameters, and we've already got users coming into the facilities. Again, it's a pan-European project. It's an international facility that's in fact owned by a number of countries, including the 2 hosts. We have Germany, Italy, Lithuania, which is a real leader in laser science, Bulgaria, and the UK as well. And we expect other countries to join as we now are forming ELI as an international organization. So we're establishing ELI as what's called a European research infrastructure. That's a kind of legal entity that we have in Europe to really allow it to be pan-European and move across country borders. There are some specific advantages to that. Specifically, it means that countries can join. It's not a collaboration of labs, but it's truly countries and ministries that get involved and co-fund the facility. This is the easiest and most convenient legal mechanism in Europe for this, and it was designed specifically for this purpose, and it's governed by a European regulation, which is the highest form of European law that we have under the EC Treaty. The member countries support it. It offers a lot of legal flexibility. As an organization, we have a lot of flexibility in terms of procurement rules, which is quite useful in terms of being able to procure performance-oriented equipment. And we also have some tax advantages as well. Even though it's a European facility, it's also open for non-European facilities to join, or non-European countries to join as well. And we encourage that, and we're talking with a number of countries right now about joining. And you can join as a member or as an observer, or even it's possible to become a strategic partner, in which case there may be some very specific strategic, let's say, scientific reason for establishing a partnership that doesn't necessarily have to do with the country, but it could even be at the institutional level. So it's an open facility, which means that scientific access is very important. It's a user-based facility like a synchrotron or like a neutron facility. So we invite users to submit proposals. It's peer-reviewed, and then depending on the originality, excellence, quality of the proposals, then the users come, and there's no cost to use the facility. The only condition is that it's open publication rule. And eventually the data is also managed by us over the long term, and will be eventually, after a 3 to 5 year embargo period, open to other researchers to integrate into their own research if they like. In addition to that, we also have proprietary access for industry. We encourage industry to think about ways in which they can benefit from the facilities as well. And of course, because they pay for access, then their data is private, and they take it home with them. There's another form of access that's a kind of a new approach in the European Union coming into this new Horizon Europe funding period that goes from 2021 out to 2028. And that's a mission-based approach. And that's very relevant for what we're talking about today. Under the Horizon Europe mission approach, what we really see is an aim towards research that not only leads to innovation, but it's going to have certain effects on a global scale. And we particularly are looking at a couple of mission areas identified by the Commission, including cancer, climate change, healthy oceans, climate neutral cities, and healthy soil and food. So just if you think about the discussion we've had already, you can already start to see the connection to some of these research areas. And this is heavily funded. Out of a 95 million plus billion, sorry, with a B, budget for Horizon Europe, almost 50 billion is dedicated just to mission-based research. That's very important for our users because oftentimes facilities might be relatively passive and sitting back waiting to get their proposals. What this does is this causes us to lean forward more with our users, think about campaigns in ways that we want to approach these particular thematic areas. So the second pillar will, as I said, incorporate over $50 billion into this. And we're already seeing, for example, with laser-driven particle accelerators, proton therapy applications. We're also talking about and looking into transmutation and handling of nuclear fuel. And we're also looking at new approaches, as you heard earlier, relative to fusion, really leveraging a lot the developments that we see with the high-power, high repetition rate lasers that are enabling a new generation of accelerators that are laser plasma driven. So there's 3 facilities. The 3 facilities are the Eli beamlines in Prague, Eli Alps in the center there, which is located in Szeged, Hungary, and then Eli MP, which is located in Magarele, Romania, which is near just outside of Bucharest. And each of the facilities has its own particular kind of leaning. So Eli beamlines, as I'll talk about, is more focused on high energy, high field, very intensive pulses, whereas Eli Alps is focused more on high repetition rates, attosecond, ultra fast science, and then Eli MP, the MP stands for nuclear photonics. So really pushing the edge of what's possible, not only using laser-driven science, but we also have a gamma accelerator being built there, and we plan to interact those beams together and really explore what's possible when you talk about very high density energy. So right now, in the first phase, we look at transitioning the first 2 facilities, beamlines and Alps, into this Eli Eric. Eli MP is still under construction and will join at a later date. And then the idea is to really manage these facilities as a single organization from the point of view of the users and the funding. So some of the science that you see there, obviously the laser development is key for us, but in addition to that, you're also seeing radiation physics, electron acceleration, ion accelerations of different kinds. We're already with lasers reaching GeV levels. So I mean, the Bela accelerator out in California right now has already reached 8 GeV, and you're talking about very compact sources. Now there's a lot of caveats there when you compare with the traditional RF accelerator, but what we definitely see is a trend in the future towards a new generation of particle acceleration. We also see a lot of application in biology and material science as well. We're already working in the UV and the soft X-ray ranges. So plasma physics and high energy density. This is just the kind of meat and potatoes of high energy laser science. This is where we see a lot of very special research being done, also in ultra high intensity interactions, very theoretical physics as well. I'll talk about some more practical aspects today, looking at the facility in Prague, just outside of Prague, and Dolní Břežany is a suburb just outside of Prague. You just get a sense of the proportion for a laser facility. That just the laser hall itself is over 100 meters long, but it's also 4 levels deep into the ground. So we have a combination of the lasers there, and then the other building you see there are support laboratories and offices. And this is the one facility in Prague where you see the lasers at the top level. So 4 major laser sources, L1, L2, L3, and L4. So the L1 and L2 are focusing more on high repetition rate. So you can see with the L1, you're already looking at a kilohertz repetition rate, 20 hertz at the L2. What's very exciting for us, built in collaboration with Lawrence Livermore Laboratory, is the L3 Happels laser. So this is a petawatt class laser operating at 10 hertz. So this is high repetition for this level of intensity. This opens up a whole new field of research. And then of course, we're also still continuing to do experiments in the nanosecond range, 10 petawatt class laser with the L4. And then a range of beamlines as well, everything from molecular applications to X-ray sources. Secondary sources are very important for us, plasma physics, and a number of other things, including acceleration, of course. I think what's interesting to keep in mind when you look at these facilities is the sources are not segmented and parsed and operate independently. The idea is to operate them together and to be able to find different ways to combine the sources together to create new science. Just a quick look at the table, and you can see very quickly the performance where we are today as of November in 2020 relative to the design specification. So we plan to be more or less up to full specification by 2022 with all of the laser systems. Just on average across the board, we've reached about half of the intensity and design specification for most of our lasers. Importantly, L3, just recently, we already see it operating at 400 terawatts at 3 hertz. So we see some very good performance coming out of the lasers, and we're already doing, we're already doing science at the facilities, even though we're going through commissioning now. So one example which you heard a bit about already is that's come out of the Eli beamlines in Prague, is really using proton boron experiments, using the lasers to drive that. So the advantages are clear and have already been kind of enumerated there. But what's very specifically nice about this is that it's very clean as a way forward. And where we are in terms of publication, I mean, in addition to a number of publications, you can also see in the bottom right, there's already patents coming out of this technology, and we already are working with commercial partners as well. So this is, fusion, it has gone through many iterations, right? And as we say, tokamaks and ether, still a long way to go. But what I guess the point I want to make is technology is moving forward. And we're seeing steps forward. Laser science is still developing, according to Morse's law. So this is a very fast development that we see. And every time you get, to another level from a terawatt to a petawatt to 10 petawatts, you're going to see very different applications to the physics and the applications. So this is happening now. We're also doing proton boron capture therapy using the lasers. So this is very exciting for us. In particular, working with our partners at the INFN down in Italy. And again, we're not even still at full capacity or full capability yet. Now, let me shift over. I'm mindful of the time, just to kind of look briefly at the different laser sources. This is a good example of the 10 petawatt compressor. You just get a view that it's as big as a locomotive. So these are not your standard tabletop lasers. This is a different class altogether. Now, if I shift to Eli Alps, this is the facility in Szeged, also quite large facility. The experimental hall is a very similar size and capacity as the one in Prague. Both of the facilities are 30,000 square meters each and located on about 5 hectares of land, but with different focuses. So Eli Alps is a bit more spread across the surface area. As I said, we're looking at high repetition rate lasers, but we do also have a petawatt class laser, 2 petawatt, 1 hertz laser being built by Amplitude. And we're also doing a lot of work that requires heavy shielding. So one of the very interesting experiments that I'll talk about in a moment here is taking place with our kind of workhorse laser, the Silos laser, is some experiments relative to transmutation. So I'll point that out a little bit more, and then possibly Toshi will say a few more words later about that in his presentation. Just a quick glance at the facilities. all of this work is taking place in clean rooms. So that's an important point. Keep that in your mind for a moment, because when I come back to the sustainable operations of the facility, that's an important factor. We have more clean room space at our facility than all the rest of the scientific clean rooms in Hungary. So it's a quite large space. We've got more than 4,500 square meters just of ISO 7 and ISO 8 clean rooms. This is a quick table of the lasers. And we're very proud of, and we see a lot of development, particularly around the laser that you see the second and third one there, the Silos laser. This is a very special high repetition rate laser. It's also a single cycle laser. And we're really looking at pulses on the order of less than 6 femtoseconds. So this is very exciting for us, and it's important because it enables some of the science that's coming out. Again, state of the art, and built together with Lithuanian partners. And some of the companies, Expla, that's one of the leading laser companies in Lithuania. So one of the key research that we see coming out now, we've already also started to do work with transmutation. And of course, I don't need to go into now a long discussion about nuclear waste and what the issues with it are. I mean, you know, I don't even know if this is the most up-to-date or recent, but we see, you know, 270,000 metric tons of nuclear waste around the world. And then also the half-lives of the different materials. It's clearly an issue, and as many positive aspects as there are with nuclear, it's very difficult to say that it's an environmentally friendly technology when we all know very well that getting rid of this and managing this waste is a key issue. And so being able to find ways to kind of mitigate the long half-life, the long kind of radioactive half-life of the materials, and be able to dispose of the material in a much safer way is one of the key elements of, I think, nuclear being able to become, you know, back into the mainstream. And I think we're also very close to that. If we're able to lower the half-lives, then obviously we can think about the number of years that material has to be stored. Well, that is very important in terms of determining the specifications and requirements of a repository for nuclear waste. And that could considerably reduce the cost of storing the nuclear waste, but it could also, in many ways, make it somehow more acceptable to the broader public. There is already, you know, transmutation, I think, is also one of those areas of science and technology that's had its ups and downs, like fusion, over the years. It's been marginalized at times, but I think it's, again, something that we see coming really into the mainstream. And I think probably one of the reasons for, you know, historic marginalization is just that you have a heavy investment into certain kind of nuclear infrastructure installation, and these kind of approaches opens up new pathways. Just to put it in perspective, in Belgium, they're building a national project. It's not a European project. MIRA is a 1.6 billion euro infrastructure. In the first phase, it's already in process right now, started in 2019, 558 million from the Belgian government to explore this further. And if they're successful in their first phase, then they'll move on to the second phase. And it should be completed with a 600 MeV LINAC and a 100 megawatt reactor by 2036. So a lot of work in this area.
5 more minutes.
Okay, that's going to be challenging. I'll move quickly. Thank you. Just a kind of a quick overview of the transmutation. So this is an idea that came out of Professor Tajima and Gerard Moreau's scheme for a neutron source for laser-based transmutation. So really it's a laser-based neutron source, because in order to be able to achieve the transmutation, we'll have to be able to achieve first a very efficient acceleration with the protons to be able to drive the neutrons. And really it's the development of the high repetition rate lasers that's starting to enable this. So we're doing experiments with the University of Szeged. This is a Hungarian funded project at Eli Alps. And they're looking at the fusion that can be really first the neutron generation. We're developing target systems to be able to understand what the best materials are for that. And then we're looking at the right kind of setup of the laser to be able to do that. So of course, as we're aiming for this mission of transmutation, we're also pushing again the limits of what we can do with the laser. So this is not something that it's not a zero-sum game. We make progress with lasers as we aim towards this higher mission. We've done an experiment last year already with a number of different materials. We were able to generate protons and deuterons with just about everything that we tested from the materials. But what was particularly interesting with carbon was that we were able to very efficiently in the kind of 5 nanometer range targets generate a considerable number of protons, 10 to the 12 steroradians. So it really it proves to us that this is good. We're moving in the right direction. We see signs that we can efficiently generate protons at a useful MEV, and that will lead to neutrons. Just a few words in the last minutes that I have, because this is one of the most the points I really wanted to make. When we're using these large-scale facilities, there doesn't really need to be a trade-off between performance and sustainability. Already nearly 11 years ago, a group of European research infrastructures, including CERN, PSI, ELI, the European Spallation Source, started getting together on a bi-yearly basis to have workshops where we look at how to manage the operations of these large-scale facilities more sustainably. In our case, funny enough, it's not really the lasers that are the major issue for us in terms of energy use. Our energy use is being driven by the size of the clean rooms. Now, the reason for that is we're using almost 5 megawatts of power just to cool and keep clean the clean rooms. And we have to expand that to 8 megawatts. So a large portion of our energy usage is really coming from keeping the clean rooms cool and temperature managed. So one of the advantages that we see in this is that, of course, we're in a place where there's a lot of sun, so that makes it difficult to cool. But if 85% of our energy use is just from HVAC in a very sunny area, then what could be a solution to that? And it's a bit counterintuitive. What we've seen from having to clean out and cool these clean rooms is that Szeged actually is in one of the sunniest areas of Central Europe. And really we have a solar isolation potential there for solar, but what we also think is that solar photovoltaic is not really an efficient approach for cooling. It's just simply the energy density for cooling is not there. So what we would like to see is there a way that we could take advantage of the solar radiation to do cooling. And again, I'm not talking about compressor-based air conditioners, but what we're really talking about is thermal-based cooling. And when you look across the world and you see where energy is being used, and while it's true we tend to focus on things like transport, et cetera, what we see really is more than half of all the energy being used in the world is used for heating and cooling. And that trend is probably not going to go down. So we thought, well, we need to really take a closer look at what this means for our facility, as most of the energy demand that we also see is related to cooling. And so what we've decided to do is look at a solar cooling system that's thermal based. So it's an absorption based cooling system that relies on the sun in the summer to be able to help us cool the facility, and particularly to cool the clean rooms. And what we see is it has a much higher cost of performance, or coefficient of performance, than the compression chiller-based system that we had originally installed. We believe that we can reduce the energy consumption on the cooling system by up to 80%, and we're able to also have a much more reliable operation in the sense that these absorption-based chillers tend to be much more long-term in terms of they don't wear out as fast as compression-based systems. So basically, these are lithium bromide systems, which is a very important desiccant, and we use just thermal collectors to be able to collect the heat up to 88 degrees, and then based on that, our chillers can use that to cool it down to as much as 7 degrees Celsius. And that, what this does is it not only takes away the heat, but it also takes away a good bit of the humidity, which is important for us. So without going into the different kind of collector types, what I just want to say is this allows us to use very straightforward, basic thermal heat collectors. These are not fancy state-of-the-art photovoltaic collectors. These are really just off-the-shelf, large-scale industrial collectors. We have a capacity for almost 20,000 square meters of collection at Eli, so that's an advantage based, relative to our site. And we think that we have the capacity for up to 14 megawatts of thermal capacity from this system. Okay, so maybe just to kind of close out, the important thing for us when we look at the operations, this does one other critical thing. It actually freezes our energy costs around the cooling, because one of the things we as a public facility have to worry about are the rise in energy costs over the next, let's say, 10 to 15 years. what we see is not only will we get a payback in less than 15 years, but we also see that we'll be able to freeze those costs. So that payback is based on a 2020 euro value. And as we see the euro change and as we see energy costs go up, we expect that this will give us not only a saving, but more importantly, it'll give us stability in terms of energy cost. So the last part about that is, in addition to that, around the Eli facility, where there will be a large industrial scientific park built. And so this system, while we'll pilot it at Eli Alps, it should also apply for a much larger kind of area that will encompass several hectares and probably 20 to 30 different scientific labs and research-oriented companies. So that's the advantages of the solar thermal. We're very happy with this approach, and we're talking with other labs that also use energy recovery techniques from their machines and are thinking about integrating this into their facilities. So we think that there's a significant trend at the large RIs in Europe towards sustainability, also in the research as a criteria for scientific evaluation, as I pointed out. But I think there's also a growing insistence among stakeholders and even our users that we need to be more sustainable and we need to rethink our operations. And so a number of large-scale facilities, including Eli, are doing that at this time. So I think that's it. Thank you very much. And I appreciate the extra minute or so, Professor Sergey. Thank you.
We unfortunately we don't have time for questions. So maybe in the chat if any.
Thank you very much.
And now we are moving to the last talk of our forum. It will be given by our co-chair, Toshi Tajima. Toshi, please, your talk. Toshi, you should switch on your. Oh, okay. Yeah.
Do you hear me?
Yes.
Okay, great. Thank you. Thank you for 9 speakers preceding me, and I can stand on your shoulders. In fact, not only you guys, 9 people, but exactly 65 years ago, 1956, the people from East and West gathered to discuss about atoms for peace, as you know, right? In which fusion was declassified. A collective accelerator idea from Budka Institute, Wexler, discussed about plasma-based accelerator, very compact, or should have been a very compact accelerator. Instead of $100 billion, 100 kilometer size accelerator, maybe on your palm top. That was the visions and the aspirations which have been discussed 65 years ago in Geneva. Here we again, East meets West, but this time to tackle global energy crisis that you guys, 9 speakers have spoken about. And it is very urgent. So that's what I would like to contribute to. Okay, so how do I go? Yeah. So even myself, to the right of this picture is my 1 block away from my house, which was devastated by the very dry and hot weather in Southern California, October fire. This was because of the western part of the continent. In this case, North America continent is very dry and hot, whereas the east part of the continent, such as the eastern part of the Europe and Asia continent, opposite happens. Very dry and very drenching rain and also warm weather, which causes like a flood. And in this conference, the northern part of the continent suffers the melting of a tundra and associated troubles. So these are already manifesting in our own daily life. In my case, I have to be mandatorily evacuated from my house to avoid this fire due to the very dry and hot weather in California. So here I would like to make a few examples of how we can cope with this crisis. First one is I'm going to recapitulate that Michael Bindawar was discussed about fusion. by a neutronic path that my mentor, as well as his mentor, Professor Norman Rostock, followed this declassified fusion since 1956. Second item is the kind of thing that's similar to what Stepan already talked about, what I called characterize to institute a toilet in nuclear energy. Toilet, in this case, you generate radioactive nuclear waste, but we usually do not care about too much. Only you care about energy production, which is the forward side of the science. That's like a kitchen instead of toilet. Toilet is left out, but we now have to address our toilet of the nuclear energy. So that's what I'm addressing. Some of the speakers have already spoken, nuclear transmutation. Third item is again the brainchild of 1956 by Wechsler from Butker, who advocated the plasma-based accelerator, collective accelerator, which I also followed his inspiration. And then also I would like to follow by looking at the tall trees in California. Well, the tallest tree happened to be in California. So this I call the bio-inspiration in nuclear energy. Okay, I'm gonna make an artificial tree, which is driven by nuclear energy. So these are some of the outline that we can think about it. As Michael Binderberg talked about, based on the declassified fusion research 1956, well, okay, some of you also mentioned the fusion is always 30 years away from now. But if you do, like Norman Rostock mentioned, end-in-mind research, and also a neutronic type of fusion, it can compress the research length by large amount. And it has certain new ideas, which I call the bicycle-like stabilization. Bicycle is unstable if you don't pedal, but if you pedal sufficiently hard enough, this kind of left or right falling to appropriate indefinite length of the riding on the bicycle, right? So this is the kind of a technology that we are now witnessing that you can create by a relatively simple geometry, as Michael Binderberg mentioned, but driven by the particle, high energy particles. High energy particle can do two things. One is that because the energy is high by accelerated particle such as 100 keV or slightly less than 100 keV, you can make energy already high enough to cause the fusion without worry about too much of heating. Other thing is that also it will like a bicycle tire to make a spinning bicycle tire to be stable as a plasma stabilizer. So these are the new ideas, and then also embedded in pioneers such as Norman Rostock, and then we are realizing it very fast because the beam is available and you don't have to go by heating up a long time. Okay, so that's the one idea already talked about. I don't have to go deeper than that. Second idea we can utilize to address our crisis is to institute a toilet to nuclear energy, which I mentioned already to an extent. And then the Stepan and then Lee have mentioned also already. So instead of a kitchen side of the nuclear energy only, we have to take care of a toilet side of the nuclear energy, which is the transmutating, specifically damaging high, long-lived nuclear waste. And that can be done by high energy neutrons presence. High energy neutrons can be created once again, as some of you already mentioned, Stepan in particular. You can utilize nuclear reactions. Usually people think about using nuclear reactors, nuclear reactions, but we can drive the beam and beam-driven fusion. Low energy beam is sufficient to trigger the fusion-based neutrons. So these are the new science in 21st century, apart starting from 20th century science like Einstein here, who have done the great science push in the kitchen side of the science. But now we need to take care of the toilet side of the science as well. So we are going to do the toilet science of this, such as this kind of deep burial facility on Kalo in Finland to be become much safer and long-lasting, and then ensuring the safety and the reduction of the toxicity. This picture has been mentioned at least 3 times by now, so I'm going to skip, but how you can reduce the toxicity and the volume of this by 100 to 1,000 times by transmutation, right? So I have to skip that. Main important part of the relatively energetic neutrons, which some of you mentioned, such as Stepan, is that this diagram, for example, if the neutron energy is greater than MeV, which is a 10 to the 0 MeV here, then the neutron has a specific fission-driven capability over absorption of the neutrons. So that's why we needed some presence of energetic neutrons to maintain the transmutation in the proper direction. If you do that by fusion, the Allen mentioned that you can make a cheap laser, efficient laser conversion of accelerating deuterons into a beam of 100 kV. 100 kV deuteron beam can cause copious 14 MeV neutrons, order of 100 times energy catapulting, and this can cause 200 MeV fission. So you get this kind of energy catapulting that will cause the reduction of the expensive accelerator-driven neutron production. I'm not going to the detail of this because I think we don't want to spend too much time in the details. And some of you, like Stepan's talk, have already mentioned about the plutonium importance and then how to kill the americium, neptunium, and curium, etc. So we don't go into the detail of this, how we want to reduce some of the minor actinide by the neutron, high energy side of the neutrons coming from fusion, for example. And then they try to reduce or take out the fission products so that you don't get stopping of the fission products of the transmutation. So these are some of the technical challenges we have to address in order to make a transmutation process to go forward. So which we did studied, as Alan also mentioned kindly. Okay, so we have invented a certain operation stand, which is what I call the go liquid. Instead of solid-based fission reactor concept, which is what Enrico Fermi in 1940s started, and because of his rapid success in only 4 years in the Chicago pile, what is I call the technology collapse happened. In other words, all the nuclear engineering has to be like what Enrico Fermi did. That is solid operational engineering of the nuclear reactors. But there is a way to make a liquid operation, such as molten salt. And if you do that in operation in liquid, you have a much more amenable way to operate in a safe way and avoid what Lee said, the runaway operation. Avoid the runaway operation because the molten salt is a liquid. So if you have begin to chain react, liquid will automatically expand and then they go down below critical, etc., etc. There are just not one. There are many other operational embedded safety functions by go liquid. Other liquid property is the laser can penetrate through and you can measure or you can monitor the reactions in less than nanosecond type of time scale. And also we can make a very compact neutron source by penetrating inside, and then you get creation of the neutron in situ in a very, very tiny way. So you have not just one neutron source, but thousands of neutron sources by thousands of fiber laser injection, et cetera, okay? I don't go into the detail. And it also, because of this, time scales are now compressed between the mechanical types of injection or takeout of the created fission products and the input of the fuel. And on the other hand, the nuclear reaction, which is this much faster timescale. These are disparate timescales, which are now can be converged into the common timescales because of the liquid operation. These are some highly technical points. I don't go into the details, but which allows us to make a monitor and feedback control to be realistic. As Bindabauer mentioned, AI control is very important in the nuclear engineering. And this convergence of two timescales, of the mechanical timescale on one hand and the nuclear timescale on the other, now begins to become overlapping. And if you do have overlapping, then you have a monitor and feedback control through AI adoption. So we are beginning to demonstrate that kind of thing in one example here. Again, I don't have time to demonstrate to you how to do it, but this is one example of how we can make instituting feedback control mechanism through AI so that you don't have any runaway or any disruptive operational dangers by this kind of nuclear technology. Okay, so last 2 points, I have to go quickly. Collective accelerator is one of the very cardinal, interesting idea and inspiration came out of 1956 Wexler's talk at the Geneva, the same thing. And this one made Norman Rostocker to work on the collective accelerator and compactifying it. And Dawson and I happened to come with the laser accelerator, which Alan mentioned. And this can make this kind of huge accelerator to be on your palm size, which is being structured into the research in Alan's labs. So using this, well, this is again Alan mentioned about some of the Hungarian. In this particular case, the left is the Hungarian president, got interested in this type of research. So we are beginning to work with them at Eli Alps. Again, I don't go into the details, but we are able to demonstrate this kind of laser in a very compact, small, millijoule operation, have a 75% efficiency from laser to the deuterium ions. This is just artificial simulation showing nanometric foil creating millimeter target in a millijoule type of operation. And you can make thousands of that in one set of transmutator. So that subject I'd like to mention is to learn from our biosphere. You may call it the bio-inspired nuclear energy, or we will try to create artificial tree. How do we do that? Well, if we try to make a carbon negative, some of you mentioned that it's not enough to be carbon neutral because ice melting process is so slow that we may have to go negative. Okay, if we do, well, one thing is that like learning from the tree. Tree is, of course, absorbing CO2 and the return to the oxygen, right? So if we try to learn from the tree, this is the highest tree in the world, Sequoia tree in California, well, we can get the inspiration of how can we make a tree-like way of nuclear energy operation. First of all, nanotube can pump the water more than 10 meters. This is more than 10 meters high without any pumping operation. You don't need to provide any pumping because it's the surface tension of the nanotube will pump the water up more than 10 meters without a problem. Permit thin film of nanotube in the leaves can permit the photons penetrate to make a chemistry. So if we can make artificial tree in carbon nanotubes with the adjacent to the radiation abundant nuclear reactors, such as the fusion reactors or transmutator, based on these giants like Ryogo Kubo or Ilya Prigozhin, on the bunch of material scientist giants, we can design artificial tree for nuclear energy or toilet over nuclear energy. So some of the ideas, I don't think I have too much time, but there are lots of carbon-based walls, such as graphene or carbon nanotubes. Heat transport efficiency is very, very high. Heat conductivity is extremely high, in fact, higher than the metal. Strength is very, very strong, the metal in the direction of tensile. Bending is very flexible, on the other hand. Neutron damage is the least. Chemical corrosion is the least. Replaceability, safety, and etc. So this is one of those graphs. I don't have time to explain to you, but we can compare the metallic materials with carbon materials, very different in a good way. This is another table I don't have time to go through, but again, metal versus carbon-based material. Many of the neutron damage, neutron activation, corrosion, chemical corrosion, and physical property, orders of magnitude superior. Why do they not use these materials? I don't understand it. Well, I guess I understand it. The metals are easy to make, and our civilization 20 centuries ago or 40 centuries ago discovered metal first. Again, the technology collapsed to the metal. But now we know the carbon technology, or we get the bio-inspirations, right? So bio-inspired wall has very abundant, interesting features, which you might try to make fusion reactors more safe or more realistic, or you can go carbon negative from this transmutator or carbon fusion reactors. So these are some of the benefits by going a bio-inspired wall. So in summary, I hope I went very fast, but nonetheless, try to take a spirit of 75 years ago of our fathers or grandfathers who met East and West and Geneva to start atoms for peace. Now we are talking about science for global warming crisis solution. Also, it was 65 years ago, the collective acceleration was suggested. We now reap this kind of ideas finally materialized, such as Alan mentioned, in the Eli, in a very, very convincing ways, and making an accelerator of the GeV in the centimeter instead of 100 meters, etc. GeV proton accelerator hundreds again meters to make a transmutator. Now we get millimeter, etc. So we get this 65 years of the previous predecessors. We are now standing their shoulders to address even higher, or graver crisis. In neutronic fusion, total science for nuclear energy, compact neutron source to drive neutrons from the fusion by efficient laser-driven acceleration, bio-inspiration to make such reactors like fusion or transmutator to be compact, not only compact, but we shall find a path toward carbon negativity utilizing these radiations coming out of the fusion reactors or bio-inspired transmutator interior radiations to trigger, to make CO2 or methane to be decomposed into something less damaging to our environment, or convert collected CO2 from your chimneys into something safer. So these are some of the artificial trees we can construct based on the bio-inspirations. Thank you very much.
Thank you very much, Toshi. Any questions to our co-chair? No questions, probably. Toshi, probably people are quite tired already.
Yeah, I know. Yeah.
And just instead of answering questions, Toshi, maybe we can ask you to make some conclusion remarks about all our forum.
Oh, okay. So if you don't have any specific question on mind, I'm glad that I may have even understandable presentation, or it was too fast and then it skipped over your head. I don't know which one. Anyway, besides that, back to looking at 10 talks. Well, first of all, I would like to thank, of course, Sasha's invitation to begin with 2 years ago, that he suggested, well, Toshi, you should start organizing forum on the climate crisis and the energy issue. And so I accepted that, but then I reply to him by, okay, we would like to make Uspehi as our back review article collector, because just passing the talks are not enough for addressing the crisis you guys have already discussed. We have to permanently fix the view and the methods that you collected, evidence, and perhaps the solutions. These have to be not just talked about, but has to be recorded. Not only recorded, but we should have constructive discussions among each other. Now we know each other's philosophy, not only philosophy, but actual work and the discoveries, right? Based on these mutual interactions and network, we should work together, just like 65 years ago, East and West met and created new science. And we are still standing on those new sciences 65 years ago that the people have gathered. My mentor is one of them who learned from that 65 years ago meeting, inspired by that. I'm already inspired by you guys' 9-10 talks. But we should not just a passing inspiration, but we should connect and make a network of ideas to construct ideas even deeper and higher, number one. Number two, as Alan said, we should implement such ideas into partnership or network collected work. There are a lot of infrastructures. Again, Alan mentioned he's providing even this $80 billion of the money fund, or there are other ways that we could try. And in each country, West and East, may have different operational principles, but we share the same grave outcome of the climate changes now. And we learned some of the climate crises are imminent or even accelerating or close to at the point of no return. and if it is even carbon neutral, right? Maybe we have to even go carbon negative. I don't know that for sure, but at least we are providing, even though currently it's just ideas level or just rudimental, even we could think about carbon negative as well as carbon neutrality. So that's my short summary myself. I may be too bold summary, but anyway, let me put that on you.
Can I ask Toshi one question?
Yes, please.
Before you close, you didn't talk. There was an interesting talk about the geoengineering.
Yes.
And there is a mixed opinion about it. What's your own thoughts about this?
Okay, engineering is necessary, first of all, I would say. And then applying engineering thought and practice on the geophysics and geology, if I understand correctly, is the geoengineering, which probably becomes necessary. I think what is the question that some people are worried is that when you apply the engineering thought on the geophysics or geography, it is a huge endeavor. So that's why it is, sometimes if you do it wrong, it will cause even more damage than the doing good, right? That's the potential concern. I understand that fully. So we have to create a correct solution and then do it right way if we do the geoengineering. Now, I'm slightly less ambitious than geoengineering, but I'm a bioengineering, or at least learning the biology to make a bio-inspired engineering. So I'm a bit lower in the food chain.
No, that's a different story, right? Bioengineering is a local thing. Geoengineering is a global thing.
That's right, yeah. So I want to make a sort of a bioengineered nuclear energy or fusion or transmutator. So if that becomes useful, I'm happy. And if it is useful, then the government or a large body of scientists agree on to implement it for the purpose of geoengineering. But okay, there are steps, right? You have to first understand that what we are doing. You don't want to do it before you understand what you're doing.
So
that's for sure.
Is somebody willing to tell something? No more comments. So I think that we have to conclude our meeting, and I would like to thank all speakers for their contribution to this event. Actually, it was very interesting and very diverse, but in some sense, it demonstrated some unique features of our nature. For example, I got that carbon is getting more and more popular. We discussed carbon in Arctic and carbon in nanotubes.
Right, yeah.
And actually, probably I'm a bit selfish, as I think other physicists who participate in this meeting, because we think that physics is just the science to bring all other neighboring sciences together. That's why Valery, we asked him to give the page of Physics Успехи to publish the talks of this meeting. I think that we have to thank especially Toshi, because Toshi was actually an engine behind organization of this event, and I have to confess to the people probably still just participating in our forum, but not direct speakers, that Toshi collected us so many times in his Zoom conferences that actually sometimes on Monday I feel myself not just in the proper condition. If Toshi doesn't call us that let's speak again about this forum. Well, of course it is a joke, but I would like to suggest to all of us to make to digest a bit what we heard today, and maybe Toshi in couple of weeks you can again invite us to your Zoom conference, and we will discuss what we took from this event, and probably we can also plan something for the future. Well, of course, we have two quite different portions today, climate and energy, but of course the idea is to make them closer and to see the influence in both directions.
I think it did. Wasn't that? That was clear to me.
Well, I think that maybe in, but again, let's us digest a bit and to make some suggestion for ourselves for the future.
Yeah.
Probably we will propose some kind of continuation, because of course the topic is very diverse, very diverse, and we certainly can concentrate on some specific areas, or just to discuss these more interlinks between these two problems. So I would say honestly that for me it was very useful. So I know many people and almost all speakers.
Yeah, so it was to me as well.
It was very useful to hear just these opinions, and let's think that it is our it has been our first effort, but not the last. At least I think that I personally will miss just if we don't come together again. So
Yeah.
thank you very much. And
So let me do two things. Say two things. One is before we forget, our brain. Well, I should say my brain is very good at forgetting things. Okay. So before I forget, and hopefully you don't forget as quickly as I do, but before you forget, I would like to urge you, all of the speakers, to write up what you talked into review of what your thoughts, and then they write a review paper and they submit to Valerie for his journal, so that it can be collected and permanently fixed as a review of entire thoughts as 10 speakers, or with co-authors included, more than 10 authors. So that's a short-term action I would like to suggest we should write, and we have to have some kind of deadline. We talked about in the previous Zoom conference 2 weeks ago, I think, that such a date should be end of March as a possible deadline. So that's a short-term proposition that before we forget, we should write what we said.
Toshi, and I think that we will be also coordinated by our website.
Mm-hmm.
I think we will ask Sergei Malenko just to support this website.
Yeah.
And
okay, so these are the speakers, but slides will be uploaded in the website. Is that right? Yeah. So that's another short-term action, right? but those are only short-term actions. I think a longer-term actions could be, like Alan invited almost, like he is waiting for us to eat up his fund, right? $80 billion.
Yeah.
He wants for us to eat, right? So you should chew up some chunk of 80 billion. You have to be a good one to eat. You know, if you're lousy, you can't eat 80 billion.
Well, okay, if there are no more comments, so Toshi, please stay our engine, and our topic is infinite.
Yeah, thank you for you guys staying up until 1 o'clock or even 2 a.m. in your time, and the Siberia it's 4 o'clock.
Thank you.
Thank you for camaraderie.
Very much.
Bye.
Good night.
Stay safe.
Bye-bye.
Thank you very much and bye-bye.
Bye.
Hey.
Thank you. Bye.
Thank you. Bye-bye.
Ciao.
Bye, Toshi.
Bye.
Hello, Alice. Now I see you.